So good morning, everyone, and welcome to this international workshop on synchrotron spectroscopic tools to study metals in biology. So I will first like to introduce the people that I have the honor to have here today. So Dr. Jose Mustre, the General Director of Synchrotron. And we have Dr. Niels Schutt, the FG Postdoctoral Fellow at the Department of Chemistry here at Synchrotron. And Dr. Mario Delgado Jaime from the University of Guadalajara. And I'm very happy that we are organizing this very first event after the pandemic. And I want you to know that Mario and Niels helped me organize and put together this workshop. And in this workshop, we're really putting together two passions for science that we share. One is metals in biology. So as you know, I'm always very vocal about the importance of metal ions and how they are essential as active sites of enzymes that support life on Earth the way we know it. And it also has implications, metal ions in health and disease, in medicine, in toxicology, environmental studies, origin of life, evolution, and of course we can talk here all morning about this. The metals in biology community worldwide, it's a big community and it keeps growing. And I'm hoping this kind of events will convince more and more people in the biological sciences to study metal ions. So I expect this community to keep growing. And the other passion in science that we share here in this workshop is the passion for the use of synchrotron spectroscopic tools to study metals in biology. And this is a passion that Mario and Niels share because it's their expertise and they have been trained as scientists in this area of using synchrotron-based spectroscopies and basically using these X-rays from synchrotron sources to shed light in the active sites, the nature of these active sites, coordination, number, speciation, and so on, and so that we can understand how these metal ions work in biological systems. I want you to know that this workshop was a big success. We had almost 80 registrations. Of course, you don't see 80 people here because then we were very lucky that we are being streamed by the YouTube channel. And I take the opportunity to say hi to all the people that are joining us by YouTube. And it's a really nice mix of people registered for this workshop. We had 20% undergraduates, 12% master students, 37 PhDs, 24% researchers and professors, and the rest, a smaller percent of postdocs and also research technicians. Half of the people in the workshop work in metals in biology, and the other half work on other things. And only 15% of the people registered are synchrotron users. So we're reaching out in this workshop to that 85% of people that are here with us just to learn about synchrotron-based tools, but also that they can see, because about 30% of the registrants said, I don't use synchrotron, but I think it might be useful in my project. And this is really the main aim of organizing this workshop, making sure that people know that these tools exist and that they can apply them in their research projects, and make sure that the synchrotron users community in Mexico grows, which is something that I know that Dr. Mustre shares with us. Yeah, so I just want to thank very briefly SIMBA staff, of course, the support from our director and also from the chemistry department to organize this workshop. Also from CONACYT and ECOS North through a project that made possible to have our speaker from France that in a minute I will introduce. And before going on, I will give the microphone to Dr. Jose Mustre, who will help us inaugurate this workshop.
Well, thank you very much. For me, really, it's a great pleasure and honor to be inaugurating this workshop. I normally have to say this for every event that we have in Symbesa, but in this case, I really mean it. Part of that is that, well, I myself, I am user of synchrotron techniques since before arriving at Symbesta. And actually, I have a very few slides just to let you know that the themes that you will be covering in this workshop are things that we have been doing in Simvestab for several years, or in some cases, more than 30 years or so. And that actually there is a not too visible, but a fairly large community in Simvestab of people that have this training and that have used synchrotron radiation, several aspects of X-ray spectroscopy to solve important problems. And one of the examples is, of course, here Liliana, but in actually basically all of our campuses, we have people that have been involved in some sense in synchrotron radiation. Some of them actually are graduates that obtained their doctoral degree at doing stays at the synchrotron sources, and that actually still do that. For example, in Simvestab Querétaro, we have some people, and now in our unit in Irapuato, in Langevio, there are people that do protein crystallography and are working there since a few years ago. And well, the place I am working on in Simvestab Merida, that's another place that we have that. The other part that for me it's really extraordinary about this workshop is that basically some of the participants are people that I have collaborated or I know for almost maybe in some cases more than 30 years. So that have been leaders of this field. And I think they will be able to convey the excitement that brings to use X-ray spectroscopies to solve particular problems. In this case, the role of metal atoms in proteins and other biological aspects. But I think this is very general. And this is just looking at several things that I have in some of the things that they have been done in the institution. I was looking at this. This is basically an example of how you can study change of configuration in a nickel atom in a specific example. This is no biological interest. These are nickelates, and actually at that time, one of the experts is Thomas that was working in these problems. And actually, the contribution that was done here in the institution was to find out that these structural changes were not static, were dynamic. And for that reason, it was impossible to see them with very important techniques like neutron elastic scattering, for example, that is something very complementary. And in this case, actually, it opened the field to understand how magnetic transition was related to a structural transition, but the structural transition couldn't be seen. This was actually done in 2008 with in collaboration with the Argonne National Laboratory and people from the PSI in Switzerland that we still have an active collaboration, and I will talk about this in a minute. So this is one of the early examples of work that we were doing here in Simvestab related to this, and from my point of view, it was a very important work. For example, trying to understand the effect of changing the mass of the oxygen ions in this case, and why this was so anomalous. reveal a lot of about the high temperature superconductivity that at the time was a very important subject. Um, this is another thing. Is actually in this work was directly involved with Christoph. That is here is another of the participants. And it's one of the cases in which you can show that basically X-ray absorption can give you information about ordering of molecules in the liquid state. That is something that is not easy to see with other techniques. In this case, it was a very simple thing. We were trying to understand why arsenic in solution was in some sense so toxic when it was presented as arsenic free. And the conclusion was that it was related with the apparent order that water molecules had around the arsenic oxide ion that I cannot point out in here. But oh, wait, yeah. And well, the main conclusion was that the water molecules were forming some sort of a hexagonal arrangement that was actually a dynamic arrangement. It was not a static. But I think it was an important example of the information that you can get X-ray absorption. This was done in 2015, and it's another example of things that have been done and that you could do with this technique. And then another aspect that is going to be covered by Mario, and I think it's very important, is the part of another associated technique absorption that is inelastic X-ray scattering. In this case, basically in collaboration with Italian group in the Electra Synchrotron in Dresden. First, they have done measurements in another compound that was important from the point of view of superconductivity, and basically a very characteristic behavior of one of the excitations was very visible and had important implications about why material was a superconductor. And this was done in this panel that you see here is the calculation that a group in Merida did in 2019. Actually, for me, this is very difficult because it was probably one of the last things that I could do academically after being so involved with the administration of the center. But here you can see basically the same trend reproduced by this calculation. And I think this is another important thing about this workshop. Just looking at the program that you will be able to see that actually to make important advancements in this area, most of the times, besides a very old experimental part that you need to do, you will need the support of a strong theory to interpret your data. And that's one of the characteristics of the technique. And I think that's one of the advantages that our groups here have, that we have basically theoretical and experimental groups that are in close collaboration. And I think that allows us to do some things. And now I think it's one of my favorite because was one is one of that was one here in the institution, the collaboration in that it's very hard times with when we had actually this pandemic closure of everything, and finally that the groups here were working very actively. They some of the people that work in the institution never stop precisely in the problem of the pandemic. So this is work done by Niels and Liliana and Fanny, the faculty from the physiology group. And for me, this is really extraordinary because it was coordinated work done in a very hard period. About 6 months, they could prepare these samples to study the local environment of one of the molecules that we have on the cell walls that has a very big impact on the propagation of the virus. They could prepare these samples with the antibodies that they have been infected with changes on the spectrum. Oh yeah, and Edgar Morales from biochemistry. I am sorry, in some cases I maybe don't get proper credit, but I think this is from my point of view, the very important thing is just to show that even in when you have a very critical situations, we certainly had it at that time with enough enthusiasm and very hard work of a lot of people, you still can get a very nice results. And I am sorry to extend myself on this. I wish actually I could be participating on the on this workshop. I am sure that I could learn a lot, and I am very excited about this. It's just the first time that I see an event like this in our institution, and I really would like to thank the organizers. This is really a great idea. I am so glad that it's one of the first events that we have, at least in this hybrid mode, but at least that we are able to visit here now. It's just such a great feeling that I am really excited. Thank you to all of you, the people organizing this, our colleague from the University of Guadalajara. We have actually a very strong collaboration, and that's with them. I would like to say that that's another thing that they probably get out of this workshop, that all the important work that you do or you can do is work that is done in collaboration with someone else. The only way that it can have an impact, and just to let you know, basically more than 80% of the publications that our institution does, about 2,000 per year, are done with another institution. So in this case, all the institutions are our allies. We're in this together, and thank you so much for being part of this workshop. I'm sure that it would be very exciting for the students. Basically, that's all I have to say. Thank you very much.
And I have to say the Sync AC2 project was your idea. we he calls us up and he said there's a call from the Swiss Light Synchrotron and the government of Hidalgo to do COVID related projects that use synchrotron-based tools. And he had this idea, and we just went and managed to somehow do it during the pandemic. So
No, thank you. Actually, the only thing is that it's what is true is that we have been doing X-ray absorption, especially in zinc, maybe since 1992. We had experience in other things, but absolutely none of this. The important contribution of that. The intention, that's actually the idea of Liliana and Niels. For me, it was wonderful to see that this could be implemented, and actually, that's another part that the support in this case of the state government. Maybe I should say that explicitly besides the pandemic, we actually had a very hard time in the last few years with government support for science, but there are some instances in which we can get support, and I think in some cases what you can accomplish even with that little support is wonderful. Not just this example. For example, the group of Liliana is also moving to a new lab, and that we just completed last year, and it was probably the largest effort in terms of expenditure of the government, a little bit over 280 million pesos, a great part coming from CONACYT, the government of the Mexico City, but another part coming from the Ministry of Education. So even in times where things are very dire, there are some opportunities, and it's important to take advantage of those. Thank you.
thank you. So I will just quickly pass the microphone.
Yeah, so I'm going to go a little shorter, but still want to reiterate that we are very happy to have you here and have seeing all the interest in that. Maybe I'll switch fast as this is a Mexican audience, and try to be as welcoming as much. So, o sea, yo llevo ahora 4 años en México, más o menos, como usuario de Synchrotron. Y lo que yo encontré en México es una riqueza enorme de temas científicos, especialmente la biología, bioquímica, biofísica, que es más mi fuerte, que podría beneficiar muchísimo de usar usar lugares de Synchrotron y espectroscopía de Synchrotron. Entonces, espero que ese workshop sea un núcleo, un seed que podría hacer crecer más esa comunidad que en mi opinión se requiere en México y podría tener muchos beneficios, como lo mencionó el doctor Lustre. Entonces, pues, muchas gracias and welcome.
Well, as has been said, thank you everyone that is attending this workshop. For me, I have seen the benefits of organizing this kind of workshops in small groups and small communities. Is something that I have been doing for many years now, but never here in Mexico. So it's a great idea that this is the first one of hopefully many to come, and incorporating more elements to it. This time it will be more focused on the structure, but it could be more electronic structure, which is also an important element. So I completely agree with what has been said about being a great idea to next workshop, and I'm very happy to be part of this. Yeah.
So no, thanks to you for getting on board for this. And so with this, I guess we can declare inaugurated this international workshop.
Sorry
And
for the formality, but I think it doesn't matter if we get up or not. We formally declare inaugurated this workshop on synchrotron-based spectroscopy to study metals in biology. Thank you.
yeah, so formalities is not our strength. So I'm just gonna keep sitting here to introduce our first speaker. So he's Professor Christoph Den Auer, and we're very happy to have him here. He comes from the University Côte d'Azur, from the Institute of Chemistry of Nice. So I will tell you just a few highlights from his CV. He did his PhD thesis at the Paris X1 Orsay University, and also part of his PhD was done at McGill University in Montreal, in Canada. He then did a postdoctorate stay at CA Marcoulais. I don't know if I know how to pronounce this, also in the University of Paris. And then he held up for a long time a permanent position at CEA. Then in 2002, he had a Curie Fellowship to do a research visit at Los Alamos National Laboratory and also Stanford Synchrotron Radiation Laboratory. So hence the Stanford connection that I think he will tell you very soon. And well, he's now a deputy director of the Institute of Chemistry of Nice at the University Côte d'Azur. And he's here, I should say, thanks to the support of the National Council for Science and Technology through this ECOS Nord call, which is a collaborative grant for scientific exchange between Mexico and France. And talking about taking advantage of the few opportunities that there are and the few calls that are these days to support science in Mexico. I can proudly tell you that there were only 10 projects approved this year. 2 of them were granted to Simba and both of them to the chemistry department. So one of them is this that allows us to organize this and have Christoph with us today. And the other one is from our theoretical chemist colleagues. So with this, now I think we're getting up from here, and thank you for your presence, and thank you, Christoph, for making the trip. I know your tight schedule. Thank you for being with us today.
Thank you, Liliana.
I would have to apologize. Just a little before 11, I would have to leave. This recognition for the workers of Simba staff that now are 20 or more years working for the institution. I apologize for that, but at least I would stick for the first one. I will be coming back. Try to get something.
Gracias, muchas gracias. Antes de empezar, quiero dar las gracias a Liliana y Nils y Mario para la organización de esta simposio. Y después voy a hablar en inglés. So thanks a lot. I'm very glad I could do that. Actually, I realized that what was asking Liliana, I know, apart from the science part, I never really put it together. So I was wondering which way I could introduce synchrotrons to you. And I thought, well, you know, with a lot of technical characteristics, and I'm not a particle physicist, so it might be a little bit boring. So I thought, well, maybe I should look into the history of synchrotron. And then I realized that the history of synchrotron was very complicated and not completely linear, and that I had no real not a lot of data on it. So what I chose to do is try to give you that's why I put partial, because of course it's not a complete general history of synchrotron, and I thought maybe I could put some personal memories on it. Really, it's not to tell you that I'm part of this history. That would be really too pretentious. But to try to show you that since a lot of years, we did some very funny things, and maybe I think that's a purpose to make you love synchrotrons and go there. Okay. Okay. So what we have always been trying to do is drawing structure of molecules. And so you can use several techniques to do that. Of course, you can do crystallography, which is kind of the king technique for knowing what is the arrangement of atoms. Okay. Well, that's true. Crystallography is a king technique, but it has a major drawback, and that you have to have order. Okay, if you don't have order, then you cannot do crystallography, and then you have disorder, and that's where X-ray absorption spectroscopy comes in, because you don't care if you are in an order or disordered system, and that's very important. Well, there are some other techniques if you are disordered, but anyway, so really we try to draw the atoms around. The atoms arrangements, let's say it like that. Okay, and so I will try to show you during this this talk here, how did people do that from the 19th century to today. Oops. Yes. Okay, I think we can really start the interest of synchrotron radiation with this guy that you probably know is Maxwell. You know, Maxwell is a very important physicist. He's the first one who harmonized electromagnetic fields and charged particles. He's the first one who harmonized all those important laws from Faraday, Gauss, Ampere, etc. So we are at the end of the 19th century, and Maxwell came up with these 4 equations in here. Some of them are very easy, but some of them are very difficult, at least to me. I'm not a physicist. But what I understand from those equations is that it relates the electromagnetic field, so electric field and magnetic fields, to the movement of a charged particle. And that's both ways. So if you have a charged particle that's moving in space, it will create an electromagnetic field, and reverse. If you apply an electromagnetic field to a density of charge, then it will modify this density of charge. Okay, and that's really the basis, the beginning of the synchrotron. Of course, Maxwell didn't know nothing about synchrotrons. He didn't even know what an electron was, but he knew what the charge density was. And the charge density, you have it here. Okay, you have it here as well. So in Maxwell's, if you take the Maxwell equation, you can derive and I'm sure you will do that during those 3 days, the golden Fermi rule, you can derive directly from the Maxwell equations. Well, that takes some pages of calculation, but you can still do it. Okay. And the other point is that Maxwell's equations have been written in the classical physics framework, but you can also derive them in the quantum physics framework, and then you come up with a Fermi golden rule. Okay, the next step, which is really probably the most important step at the end of the 19th century, is the discovering of X-rays. So Röntgen, which is a German physicist, was using a Crook tube. So a Crook tube was used at that time to study the cathode rays. And what is a Crooked cube is you have a difference of potential here between the cathode and the anodes, and you have a partial vacuum in here. And actually, a Crooked tube is a neon tube, okay, or a TV tube. I mean, an old TV. And they were trying to understand what was those lights coming from those rays coming from the cathode from the anode emission. Then they called it the cathode rays. And actually the Crooked cube was very important because Thomson, that you know, used it to discover the first particle of the atom, which is the electrons. So the electrons was discovered at the end of the 19th century, which is not too far, I think, from today. But anyway, so Röntgen discovered the X-rays because then, well, I won't tell you the story. It's a story really I like, but anyway, I don't have time to do that. But X-rays, Röntgen discovered that X-rays were crossing the Crooked cubes. And they were invisible, and so he decided that there were new rays. He called them X because he didn't know what they were, and that was the discovery and X-rays of X-rays. And that's probably the start of all physics of the 20th century, because when they discovered X-rays, then they discovered radioactivity, then they discovered the structure of the atoms, and they discovered the electrons nucleus, and that's the Bohr theory with the Fermi theory, etc., etc. So I really think that X-rays is really the start of modern physics and atomic physics. Okay, that's a funny image because that's the first X-ray image that Röntgen made with a hand of his wife, actually. And the story said that she got very mad when she saw that, but when she looked at that, because then for the first time in her life, I mean, in anybody's life, they could see their skeleton, which is really scary. Okay, so as I said, Thomson used the Crooked tube to discover the first, and that's very important, of course. He discovered the first particle of the atom, which is the electrons. And that's a really a real achievement. And Thomson was the head of the Cavendish Institute in Oxford. And, you know, after Thomson, you had Rutherford, who discovered the nucleus, etc., and etc. So it really opened the way for modern atomic physics. Well, Thomson was right about the electron, but he was wrong about the theory of the atoms, because he got it wrong then. Because he didn't know that the atoms had a nucleus. And that's a major point, because he got his theory of, I don't know if you know, but he got a theory of the plum pudding. So he thought an atom was a plum pudding with raisins that were the electrons. But of course, that's wrong. But he didn't know that anyway, and then that's Rutherford who discovered the nucleus of the atom and completed the picture with Bohr. Okay, so we are really at the end of the 29th century, and so now we know what an electron is. Now we're switching to the 20th century, and Schott was the first one. He's not known at all. He's a physicist as well. He's the first one who related the Maxwell equation with the electron. And so Schott really stated the basic theoretical concept of moving electrons. And in his thesis here, he was the first one to consider bunches of electrons moving in space, and electromagnetic waves going with it. Of course, he didn't know what synchrotron was yet, but he had for the first time the idea. Oops, reverse. Okay, the next man who is very important, you might know him, is Barkla. Barclay was an English physicist as well. And we are just before the war. And Barclay is very important because he's the first one to use X-rays to describe the atomic structure. But he didn't know what an atomic structure was. But he could see that moving across the periodic table, he got spectra, X-ray spectra, that were different. And so I think his work is very important because he related the Mendeleev, and as chemists we know the Mendeleev, theory, but Mendeleev, what's really nice, Mendeleev put all the atoms in the periodic table, but he didn't know what an atom was. He didn't know what a proton number was, but he had the idea before that. And Barclay is the first one who related the numbers with the position in the periodic table. Of course, we are in 1911, so we still don't know what the nucleus is. But Barclay observed those rays for each atom, and he understood that something was moving when you were moving across the periodic table. So what's funny is we use Barclay's nomenclature, K, L, M, edges, etc. And but it's not rational. Barclay put K, L, M, and I've read somewhere it's because it comes from his name. K and L. But what he said is that, well, I take the middle of the alphabet because I'm sure there will be series before and series after. So just in case, so yeah. But probably, he didn't pick any letter in the middle of the alphabet, but just K and N, K and L. Well, okay. All scientists work for posterity. So we are moving a little bit ahead. Tell me if I'm too long. Maurice de Broglie. So you don't know Maurice de Broglie, but you might know Louis de Broglie. Louis de Broglie is a French physicist, and he's the first one to relate waves with particles. And each particle has an associated wave. And so Louis de Broglie is the first one who theorized that. And Maurice was his brother. And Maurice is the first one who discovered absorption edges with photographs. So this one is very bad, but this one is better. And so you could recognize the edge in here. Well, it's difficult, but you see these lines in here. And of course, it's reversed because it's a photograph. So it's a negative print of what an edge is. So he used X-rays to shoot at metals, and then he discovered that there were lines like that. And so that's the first idea of an edge. But then he didn't know what to do with it, of course, because he didn't know the structure of the atom as well. Okay, and just next to that, Moseley is the first one who used Barclay's theory to develop what is called the Moseley law, which is really putting atoms in orders in the periodic table. So you see that within less than 10 years, everything is taking place with the atomic theory. And of course, one of the most important achievements in this story is Bohr's theory with its levels, electronic levels, etc. Okay, so now I'll focus a little bit more on spectroscopy. So what I try to do is draw a parallel between the synchrotron, the machine, okay, and the X-ray absorption spectroscopy. And that's different because I think my main message is that the synchrotron, the machine itself, was developed for physicists, not for chemists or not for spectroscopists. And spectroscopists took on those machines very recently. But those machines were designed for physicists, first of all. Okay, so Hugo Frick is the first one who measured a real absorption age. So it's reversed, and but you see it has a sense of an absorption age. So of course he tried to relate this absorption age with Barclay's levels, which is wrong. But anyway, so you see he put L, K, etc. in here, M. And that's wrong. But anyway, he's the first one who saw the structure, the fine structures, although he didn't know it, around the absorption age. And we are in 1918. The first guy who really did something very important for X-ray absorption spectroscopy is this guy. It's Ralph Kronig. He's really the first one. So he measured absorption age, and then he gave the first theory of X-ray absorption fine structure. So his theory was kind of half correct, half wrong. But anyway, at that time, he was the first one to theorize. And so I give you some details in here. But he arrived with this equation in here that doesn't really look like the exact equation that we use, but quite. You have a sine wave here. You have a sum in here and a factor in here. And that's a great achievement. That's the first time that we understood what, we could understand what the fine structure was. Following Kronig, there was Peterson. Peterson was a student of Kronig. And then another guy, pretty important, Smoluchowski, who developed these equations in here. But I won't go into the details. Okay, now a little bit of machine technique. Everything is taking place together. That's just before the Second World War, and that's a very important time for atomic physics and nuclear physics. We are in 1931, and in Berkeley, this is the first one. This is the first time two guys, Ernest Lawrence and Livingstone's, they designed a cyclotron. So you have here the design of their first cyclotron. So a cyclotron is basically a cheese box, well, French cheese box, so it's rounded, So, and you have an electric field and a magnetic field who accelerates particles. So you inject particles in the middle, and then you accelerate them. Okay. The beauty of this is, before that, how could you do particle physics? Well, how did Rutherford do particle physics? Well, Rutherford used polonium, who was discovered by Marie Curie, and polonium, is highly radioactive, so it produced alpha particles. And that's how Rutherford used alpha particles to have his theory about the nucleus. But he didn't have any accelerator, Rutherford. So the first accelerator came that time. So before creating accelerators, we were just using radioactivity to measure the structure of the atom. And so with this cyclotron, they could use particles of much higher energy, because of course, it's much easier to accelerate particles than just using particles emitted by radioactive atoms. And it's less dangerous. And so that's what they created. So that's in 1931. That's a picture that I find absolutely incredible, because you have two Nobel Prize physics in this picture. And so I don't know if you know those men. This is Lawrence here. He's tuning his cyclotrons in Berkeley. So he got a Nobel Prize for physics. This guy you probably don't know is Glenn Seaborg. Yeah, you know him. He got the Nobel Prize for chemistry. He's from Berkeley as well. He discovered plutonium, and he discovered plutonium because he could use the cyclotron from Lawrence. And that's kind of extraordinary. This guy is Oppenheimer. He didn't get the Nobel Prize, but he did something, well, good or not, but he did something very important at that time. He discovered the atomic bomb. Well, he made the first atomic bomb. And he could make the atomic, well, it's not completely true because he did make it with uranium. But he could make the atomic bomb because Seaborg discovered plutonium, because Lawrence built his cyclotron. Okay. And so in this picture, you have those three guys from Berkeley, which are probably the most important guys in physics for the 20th century, and they are together in this picture. Okay, let's leave Berkeley for a bit. We are in 1941, and that's the next very important step. Kertz is a physicist from University of Illinois, and he is going to build the first betatron. So a betatron is not a cyclotron. It only uses magnetic field and not electric field. And it accelerates electrons. That's why they called it beta, because beta was the beta radioactivity. And so this is not the cyclotron. The cyclotron is here on the table here. You see, it's very small. And so that started at the University of Illinois in 41. I have another picture here. You have Kertz. He's looking inside his betatrons. You see the small ring in here, very small. And it is the first one who saw a light coming out of this betatron, actually. At that time, it was the most powerful accelerator. Then Pollack. So General Electric was a very big company who counted a lot for physics at that time. And General Electric wanted to work on X-rays. And so they thought it might be very important. They immediately saw the relation between accelerator and X-rays. And so they helped Kertz to build larger betatrons. And that's what they did. That's a semi-MeV machine that you have here. And if you look carefully here, you have light. Okay, here, just here, coming out. That's the first synchrotron light coming out of a machine. Okay. I don't know if this guy got irradiated or what, but I think they didn't care at that time. Okay, and now we are in 1956, and they were the first one to confirm that synchrotron light was going from the ultraviolet to the hard X-rays, actually. So from 80 to 300 angstroms. Okay, so we are moving on. I mean, a big step. This is the first European accelerator. It's the first cyclotron. It's ADA. So ADA it was an Italian one built in Frascati. And it looks like that. You know, it's pretty small, but compared to the previous betatron, of course, it's much bigger. And so there was a very close collaboration between the French physicist and the Italian physicist at that time. And particle physics was done in Orsay, in the south of Paris, with the construction of the Orsay linear accelerator. That was the first accelerator in France. And so they decided very quickly to take the machine and to move it from Italy to France, because the linear accelerator in Orsay was better. And so they could inject from the linear accelerator directly in the cyclotron here. So again, they were building the cyclotron, not doing synchrotron work, but for doing colliders work, so particle physics. Okay, it had nothing to do with spectroscopy at that time. And we are in 1965. So just after the ADA, they built another one that they called ACO. in Orsay, a little bit bigger. And we are in 1965. And I can translate that. They say it's 4:30 in the morning, you see, and they say, we've put about 300 electrons in the ring, and we saw them. Physically, I mean, they saw the light of the electrons. I think that's quite, yeah. Okay, so then we are in 68, and probably the first real synchrotron machine was built in the Madison, Wisconsin. It was the Synchrotron Radiation Center. You have here a picture of the synchrotron. And this center played a real important role in synchrotron physics because they really they restarted the work with a small machine, and that's what in 68. So I don't know if you agree, but that's not too far ago. You know, it's in 68 that, well, at least for me, that they decided that they really started to build a machine dedicated to synchrotron work, but they were not doing spectroscopy at that time. Okay, the next achievements. So you remember Ralph Kronig, okay? And the next step was done with those three guys here, which are known as the fathers of EXAFS, actually, Little, Stern, and Sayers. And so with Kronig's theory of the EXAFS structure, they completed the theory, and they were the first one to have the idea of making a Fourier transform of the EXAFS spectrum. And by doing that, they were really moving forward, because doing the Fourier transform, as you will know during the 3 days, you really look in real space what is the arrangement of the atoms. So that's really important. So actually, modern EXAFS theory has been made by those three guys. That's a picture of the new ring in Orsay, ACO, 540 mega electron volts. So you see the size of a man here. So you can imagine it's a pretty big ring for that time. First beam in 1973. Again, a beam for collision, for particle physics. Of course, on the West Coast, there was the SLAC, and SPEAR started in 1972. And SPEAR was really using the same arrangement, because SLAC, which was the high particle physics from the West Coast in the US, was using his linear accelerator exactly the same way that Lal was doing in Orsay. And this is a modern view of SLAC. But the ring the SPEAR ring was built in 72, so about the same period, and was actually doing the same. So it started as well. So everything started in the 70s. That's basically it. And here you have the construction of the DCI, which is actually the ring I used when I was doing my PhD in Orsay. And it's really funny to see it like that. And so DCI was the first French ring to do high energy synchrotron work. Okay, so we are almost arriving to the present time. So the first beamline dedicated to visible ultraviolet spectroscopy in France was in 75 on ACO. Then they built it Super ACO, which was a better ring. DCI was working in 76, okay, and with only one beamline. That's the first beamline, covering 3 keV to 30 keV. That was called the D1 beamline. And I don't have the date of the spectrum, but this is, I think, was one of the first French, I don't know, I don't know in other countries, EXAF spectrum collected. And it's interesting pedagogically because you see that's a spectrum of rare earths. I don't remember which one. And you know, you have the absorption spectrum of the rare earth gas in here, and you see nothing. You see an absorption edge and then nothing. And when they cool it down, they can freeze it. And of course, it gets structured. And then what is appearing here is a fine structure. So that means that, you know, they observed that this fine structure was due to the arrangement of the atoms in space. Okay. In 1992, it was a construction of the European synchrotron in Grenoble, which is really the first third generation synchrotron, which is still running. Okay, so what is a modern synchrotron? Well, this is a picture of a drawing of Soleil in Paris. So a modern synchrotron has usually a linear accelerator, a booster, and a ring. So the ring is a storage ring. So now we use synchrotrons to produce light. Okay, but again, at that time, they were designing synchrotron to do particle physics. And so it's completely reversed because now we try to keep the electrons inside the ring as long as possible to produce light. And you have here a picture of the tunnel, the ring itself at Soleil, and here the booster here at Soleil. So I won't go into the details because I think it's not really useful, but just one slide on how does that work? Basically, you all know how does that work, but you have an electron bunch circulating inside the ring, and each time you deviate the electrons from its linear trajectory, it emits light. And you saw how it relates to the Maxwell equations because you're forcing the electron beam to deviate, and then that's when it emits light. Okay. Okay, the picture I always use for students is that, you know, you are running a bicycle and you are running too fast and you have to turn, okay? So you have two choices. Well, the choice you will probably, you know, will force to have is you will just go into the fence or whatever and you get hurt. But if you think about physics, the other choice you have is just to jump out of the bicycle. So you will lose energy, okay? And then the bicycle, you will turn by itself and you go straight, okay? That's exactly the same for the electron. You know, you force them to turn, but they are going too fast. And so the only way they have to conserve energy is to emit light, okay? So that's the way it works. And you have here a quadrupole magnet from Soleil, okay? And so the beauty of synchrotron light is, contrary to a laboratory X-ray machine, you get a continuous spectrum, okay, over the entire range of energy that is very intense. So here you have the spectrum of Soleil, ESRF, okay, and you can tune this energy. You can choose the energy. So you have synchrotrons in the world that are large, huge, small, etc., because then you choose where you want to center this energy in here. Okay. Anyway, but then you see that you have a high brilliance of photons over a very wide range of energy. So it's really a unique machine to do spectroscopy. Oops. And that's just a picture of Soleil that some of you know. So it's in Saclay. So you see, it's a big machine, but it's not a huge machine. There are much bigger ones. And it's a 2.75 GeV machine. You see 350 meters circumference. It's an average machine, let's say. Okay. So I thought maybe I could share with you some, images and how we started some of the work. So I'm not working on metals in biology. I'm sorry. Almost. Sometimes I'm just approaching it, but that's I've been caught by some other. Yeah. Okay. But anyway, so that's not how I started synchrotron work, I have to say, but nobody's perfect. And so I started synchrotron work around, I think, around 1996. And in 1996, so I was working at Lure, and this is how this is how it looked. So the basics, what is really nice, and of course we did that a long time ago, but what is really nice is that we used to do everything by hand. So we used to shape the beam by hand and do really everything by hand. And that's really nice to learn things. So I'm not saying that new machines are, well, but anyway, new machines, you do nothing by hand. You do everything with the computer. And it's good, of course, because you get better data. Okay, but you don't learn really how it works. So this was a D44 beamline. That's where I worked actually at that time. Here is the ionization chambers. So the beam was coming from right to left. From left to right. Sorry, this way. The mirrors were here. So we were moving the mirrors by hand as well. I mean motors, but and we had a little screen in here to see. So that's an old TV. You probably don't know how it looks, but But what is more funny, is that's the opening of the gate of the hutch. Yeah, don't look scared. It's there were keys, and so. We call that, I don't know how to translate that, but you could only move one key if you had the other key inside. And that's a hutch, yeah. Yeah, that's a hutch. And so the other point is we were not looking at the beam because we had no detectors for the beam. So we were doing photographs. And so this is a photograph of the beam. This is a little sketch to try to align the mirrors and know what's going on. Just to set up the numbers to cut the energy for harmonics. And what was really nice, if you didn't cut the harmonics properly, then you had two beams. You have the main beam and a dirty beam below it. Okay, so you could see it. So you had to work on it. But those photographs, we had a little laboratory where we used to develop those photographs because these are teeth photographs used by dentists. And so each time you had to run to the laboratory, develop the photographs and come back and, measure the beam size. Well, it's too large, it's too small, and then work the beam again, and then go back to the laboratory and etc. And you were doing that all night. And this is a sample cell that we used. So that was actually, we used this kind of big cell because that was the first plutonium experiment that we did in a synchrotron in France. Well, that's me. I'm sorry, but that's I'm very different now. But anyway, so trying to to put the cell in here. So I can tell you that we can't touch such a cell now. It's just impossible now. It's completely different. But we were traveling our plutonium sample directly from the lab to the synchrotron. Yeah, that was. Yeah, that was. Yeah, that was a lot of fun. Yeah. Yeah, and once I remember we measured the sample and there was no sample inside. It had disappeared, and of course we were very scared because we didn't know where. So we tried to move the cell all the way around to try if the sample would come back at some point. But, and so again, that's a picture of the how you would put the beam on. Just turn the button here, and you could put the beam on. So a very usual mistake, and I did it, of course, from students, is that you call your supervisor, and hopefully it's not during the night. I don't have beam. You know, says, did you check everything? Yeah, of course I checked everything. I don't have beam. And he comes in and said, well, you didn't turn the button. Yeah, you know, that's pretty bad for you. Okay, now I'd like to emphasize the big achievements, I think, and you recognize his name in here. And so another very, very important achievement for XAFS analysis is the beginning of the FEF code. And so the FEF code, I think, appeared, but you can correct me, in around 1991. I think that was actually, I did some research, but that's one of the first publications I found. And that was really, really important for us. And it arrived at Lure just a few years after, because it was the first time they derived the absorption spectrum in using a propagator, which is a green function. And this really helped to understand, well, this helps to calculate the XAFS spectrum very fast, very quickly, with very good approximation. And that was the first time they could derive multiple scattering calculation with very good approximation. Then they came up with a full multiple scattering formula, but that really was quite of a major step. And again, this is the Jack's paper from 91 with the first calculation. I mean, I was not the first calculation, but really the first major calculation of an XAFS spectrum. We used that. So when I was doing my PhD at Lure at that time, my supervisor actually came up to me and said, well, we received a new code from the US, you know, because they were working with John Rare. And you should try it, you know. So just, we don't know what it is, but you should try it. And so we tried it, and so that's another point, which was very funny. At that time, you could launch a calculation with this code, and you were going for lunch. And when you come back from lunch, you know, the code was over, hopefully. Okay. Now you don't even have time to look at it. It's completely done. So that was funny. So when you were trying different things, you were thinking before, because it would take 4 hours. And so very quickly we could calculate contributions from different atoms. So I think it's really the first code, and that we're still using, that really help us to understand the arrangement of the atoms, because you can directly or indirectly but see it and play with it. So that's really important. And then we worked with somebody that we know very well. It's Steve Conradson in Los Alamos and in Stanford. I did some bibliographic research. I think Steve did his first actinide spectrum in '92 in SSRL. I'm not sure, but that's the first paper I found. And so that was the beginning of actinide chemistry at the synchrotron. And actually, I met Steve then in '96 in Grenoble, where we decided to work together at SSRL, and that's how I met José Must. This is a picture of again of Lure, where you see all. So you had no computer. I mean, one computer, but the computer did nothing except, you know, acquiring the spectrum. So everything was done by hand and cables, you know, and so you know, sometimes you had to play with it. But that was, from my side, our first publication with actinides from Lure. That's Steve Conradson here. So that's in Berkeley in 2002. And we used the FEF code at that time. So with, you see here, Steve is here. Another guy that we all know is Eric Simoni, which is retired now. And we were using, sorry, oops. We were using, we were doing some grazing incidence spectra, but that's not the point. The point is that we had to use the FEF code to understand the fixture in this grazing incidence. And you can see that things can become pretty complicated. That's in 11.2 in Stanford, because we were doing a radioactive stuff. They built it a tent around the beamline, around the table. And so we had to move the detector around on it. That was quite a modern detector, actually, at Stanford. Okay, and so that's why in the publication we use a FEF8 version of the code to calculate to see when you are moving the sample. So basically the idea was to know if we had a crystal here, was to know if uranium was parallel or perpendicular to the plane. And we use the FEF code to calculate a priori the spectrum and to see if what we saw was correct or not, actually. And really without FEF, we couldn't do that. That's a picture. I can send it to you. That's in Stanford in 2008. That's Steve Conradson. And that's Juan. I don't know. I think he's working in
Stanford. He's at the Earth Science Department as a research professor.
Oh, now. Oh, okay.
He has been there now.
Okay. Yeah. Okay.
One of the first students that got a PhD with synchrotron.
Yeah. Okay. So great. And that's Aurélie, actually one of my first PhD students, and now she's a CNRS engineer in Nice. And that's the first beam of the Mars beamline. So it's very rare to see a real synchrotron beam. It looks like Star Wars, you know, but yeah, exactly. But you don't want to go in. Okay, and so really that's the beam coming out of the ring with almost no shaping of the beam, no optics, and that's why we call it a white beam. It's not because it's visible light, but because it covers the entire spectrum, so it becomes white. It's very intense. And I think I'm almost done. So just that's the opening of the Mars beamline. And so now that's a beamline that personally I use the most at Soleil. They dedicated to radioactive sample, and now it's completely modern beamline, of course. Very different from what you saw at DCI, and we don't do everything by hand now. And with this, yes, I'm done saying I've been a little bit long, sorry. Thank you. If you have questions or remarks. Yes.
Well, thank you very much.
Radiation. I'm interested in it from the X-ray crystallography point of view. But that was very interesting. But you didn't tell us what happened with the plutonium. Did you find it?
No, actually, I think we were too scared, so we just brought the sample holder back in the lab and open it in the lab. You know, and actually, we were using at that time. We were using one sample. The sample was very small. It was a few millimeters, and but the sample holder, because we were so, well, I don't know, cautious, or we didn't, you know, the sample holder was about this side, and we would put one sample and stainless steel, and so we were putting one sample in the middle, and of course sometimes the sample would slip out of the window, And that's exactly what happened.
And now a more scientific question. I know nothing almost of absorption spectroscopy, but I was wondering, can you follow the transformation of a compound? For example, if you have isomerization or something, can you go with this spectroscopy through the intermediates, for example, in the isomerization process, or you can't?
So if you have, okay, so if you have a modification, so what I didn't say, because you will learn that during those 3 days, is that you have to target one type of one atom. Okay, the spectroscopy, because it's based on core electron spectroscopy, you have to target one atom. So you look at the arrangements of atoms around one atom or one type of atom. It can be iron, it can be zinc, it can be whatever you want, but you choose, okay, a priori. Okay, so whenever you have a modification of the atomic arrangements around this target atom, which we call the central atom, you can see it, or you can follow it. You can follow it in situ. If you design the right cell, you can do whatever you want. But what I mean is the main difference with crystallography or X-ray diffusion as well is diffusion or diffraction is a global, it sees the arrangements on a large scale, okay? And it has a very hard time to see the modification in a very small scale. So you have, with crystallography, for instance, you know that if you have defects, you might not see it, because what is meaningful is arrangements on a large scale. Absorption spectroscopy is an inelastic process. So it's completely the opposite. You don't see the large scale, but you see the local scale around a central atom. So it's completely different. And actually, I don't know if it's still very popular, but people used to do crystallography and absorption spectroscopy to compare. And very often they could see different things, because crystallography see average over the large scale, and absorption spectroscopy doesn't average, but only sees around a central atom with a very small scale. So that's really the main difference.
Any more questions? We have time for a couple more questions. Don't be shy. You can ask in Spanish. Pueden preguntar en español.
This is really good. I'm very happy with wonderful.
Thank you. Thank you.
Well, if there's no more questions.
Thank you for showing.
I have
Back
more,
this
but I.
Bringing back these memories. But I think another thing that you didn't show here, but maybe it's better because it will scare new students, although it's different, is maybe the pictures of people having to sleep or not to sleep at the beam time.
Yeah, you're perfectly right. I had pictures of Steve or myself sleeping on the desk, but I didn't dare showing them. Yeah.
I was going to show him, but I had some of those.
Yeah, the point was, you know, we had, well, our design was a little bit specific because we had to sleep on the beam time because we were using radioactive stuff, and we were not allowed to go to the restrooms actually. And in Stanford, they were very, very tough because in Stanford, it was a different, they had the same, at that time, they had the same system of keys, you know, to open the hutch. And you had the key around the neck, okay, and sometimes they were the hall operator will come around, and if he found nobody on the station, he closed the experiment. So they were very rough on that. So we were obliged to sleep on the beam line, and if you wanted to go to the restroom, you had to call somebody. So yeah, we had a lot of sleeps on the beam line, but that was fun because when breakfast arrived, you were very happy.
In another comment that it was explicit from that is just how important was a cooperation between different groups all over the world with, for example, the original Italian cooperation that that you had.
Yeah.
I even in the theoretical part was the same. The last 3 months of my thesis on the code, they were in Frascati. Actually, there was a very strong Italian group in there.
Yeah, Italian were in Europe. They had a very strong school for graph theory that was very well known. It has a little bit disappeared now, but at that time they were very strong in that, and there was a specific collaboration between Lure and Frascati and Camerino. Yes. At that time, and there was really a major school of X-ray absorption theory. No, I completely agree on that, and I maybe what I wanted to say as well is I strongly believe that science is, and that's probably worse for PhD students. I mean that's my view of it. Science is before everything else a human adventure. If you can have interesting subjects or whatever, but I mean, the human adventure in science is more important than anything else, I think. And with synchrotrons, I think it's even more important because those machines, you cannot go to a synchrotron by yourself. It won't work because you need so many people to help you and to run the machine, to run the beamline, and then you have to prepare the sample, you have to ship the sample, you have to do the calculation, you have to, it takes a lot of people that put together different parts of, your chemistry, they know how to run the machine, they know their beamline, you don't know it, and et cetera, et cetera. So I really think that's a human adventure, and especially on those times, I'm not saying that those times were better, but I really like those old times where we were really, when I met Steve in France, I was a PhD, a postdoctorate, I'm hand of my PhD. He asked me to come to Stanford to do experiment. I was like, well, yeah, okay, sure. So, but where is Stanford? And so, a year after I was in Stanford doing experiments, and then we met, and that was really fundamental. And I think openings, going to different synchrotrons, meeting different groups is really fundamental. Yeah. And so I really encourage students to do that.
Yeah, one last question.
Hi, thank you very much. First of all, when we are designing the program, this was you exceeded our expectations for me. Yeah, I have one question that came to me right now. Like you showed a lot of building the stuff actually. Having the beamline set up and everything. I was wondering, maybe the more experienced users here can when was the first differentiation in scientific staff member and user? Like when we first apply for beam, like the general process for me, like the narrative for me is I have to write proposals and everything else. But when was that actually the first time? When wasn't this just your setup, and when was it the first time shared between people?
So I cannot answer for Stanford or other things. Well, of course I'm missing. I need to say that I'm missing a lot of. It's a partial history. You had synchrotrons in Japan, in Great Britain, in Germany, everywhere in the world. So this history is very complicated. I can answer for Lure because. When I finished my PhD, I was hired as a postdoc to become a beamline scientist. And that's what I did for a year and a half or something like that on the D44 beamline. So I was helping people who came, actually. And I was in 1976. And so I would say that people were applying for beam time before that, probably around I would say between the 80s and the 90s. But at Lure, people who were coming to the synchrotrons already knew a little bit about the synchrotrons, you know, and I think it's still a little bit the case. If you apply for beam time, but you have no idea about what a synchrotron is, you have very little chance to get beam time because your application won't be correctly written. And because you don't know what the issue is. Okay, so I think to answer your question, I think around the 90s, but it was a progressive, I don't know, maybe at Stanford, maybe you can answer, but it was a progressive mechanism. So, you know, people who were used to use the synchrotrons were coming very often, and then you built on from this, and you bring new people from new labs, etc. And now it's completely open, and you can apply for beam time. So of course this work has changed, because at that time it was longer. You couldn't apply for beam time for half a day or a day. It was too short because you had to position your samples, and you do that by hand as well. Yeah, and beam dumps and with photographs. So you sample, you don't know where your sample is, you don't know where your beam is. The only way to know it is to look at photographs. Now you have a prompter, and you know, you do that in a half an hour. But at that time you needed time. So yeah, I would say around the 90s, and now it's more open, of course, and you can apply for beam time. But I really advise, if you want to apply for beam time, don't do it yourself. I mean, alone. Do it with somebody who knows how to do it, and in cooperation. Yeah.
Okay, so,
Okay.
cool.
Okay. Perfect.
One comment, actually, I remember basically in 92, Stanford SSRL had this program that they call it a quick turnaround experiment. So
Yes.
you will apply for maybe
A test.
days
Yeah.
or of beam time, and they will help you basically with the setup and everything. Basically, you just have to take the samples there, and basically after doing that 3 or 4 times, then you could submit a proposal for beam time. For me, for example, it was very important because I didn't, I was really a theorist. I didn't have I knew the people that would do experiments, but I haven't done any myself at that time. I had just arrived back here in Mexico, and that was the way the first students from Synchrotron start going there. And it was very, very good. And another thing related to this is that they have these regular workshops to train students, and that was very, very good.
That's a good point that you mentioned, because I remember when I was a student, and we had a lot of workshops, but really a lot and that was the beginning of Xane's calculations. That was really the first Xane theory. The people were very interested in Xane's, and so you had this Italian school, you had the Stanford school as well with Keith, where you had the German school. And I remember being as a student being in a lot of workshops, and I have tons of papers in the office about, you know, all those workshops. Everything was done by hand, but you could learn a lot about those people who were trying to develop codes and developed a theory about all those spectra, and that was really fundamental. An exchange between students and those guys was very, very important. So yeah, you're perfectly right. Workshops were very, very important.
So we're a bit late, but I don't want to miss the student question.
Thank you. I wanted to know which are the main difference between a cyclotron and a synchrotron.
Okay, now, as far as I know, because again, I'm not a particle physicist, a cyclotron is quite a common machine that you use to accelerate protons, for instance. Okay, and where do you find cyclotrons now? Usually is in hospitals. So, well, you have cyclotrons to produce elements, but a cyclotron is a machine of the size of this room. You have different sizes of cyclotrons, of course, but they spiral. Okay, so a cyclotron accelerates particles in a spiral shape, and then the particle gets out of the cyclotron like that. So okay, so well, I don't have time to go back to the picture, but you have an acceleration of so it has to be ionic, of course, because you need to accelerate it. So deuterons, I mean, protons, you accelerate them and then you shoot them out of the cyclotron, and you use that in hospitals to cure cancers or to produce, also for cancers, we need technicians to do imaging, and technicians are produced in cyclotrons. Okay, so cyclotrons are used to produce beam to cure people. So you literally put the people at the end of the cyclotron, okay, or to produce elements that are used mainly for medicine, for medical application. A synchrotron, in synchrotron you have synchronized. A synchrotron is a machine who keeps particles at the same speed, at the same energy all the time. So formally, you have your electrons that turns in the cyclotrons, and of course, as energy conservation, since it emits light, it loses energy. Okay, so each time it turns, you just bring it some an additional energy. So this way you keep the electron bunch at the same energy forever. And so the synchrotron doesn't accelerate. I mean, it accelerates at the start with the booster, but then it keeps the electrons in the ring at the same energy to produce light. Okay, so that's a major difference. And the collider is a synchrotron, but with two beams and that are going reverse, and so to collide particles. So you see, you have cyclotrons, collider, synchrotrons.
Okay, so thank you, Christoph, for
Thank you.
such a great opening of our workshop with this history and all this. So let's thank Christoph again for a great talk.
Thank you.
And we are ready for coffee and cookies. Those of you who are watching from YouTube, I guess, go to your kitchen for some coffee. You're missing the fun. And we'll be back here at 11:15 as the program stays.
Okay. Oh, wonderful. Yes, yes.
So our next speaker is Dr. Thomas Kroll, who is coming from Stanford. So from SLAC and Stanford Synchrotron radiation light source. So Thomas grew up in Germany, in Münster, and he did his undergrad studies and also obtained his diploma from the Technical University of Aachen, where he studied cuprates, and later moved to University of Dresden, where he started to explore the structure of superconductive materials at high temperature. High temperature meaning 5 Kelvin. So not so high, but at the time it was considered high. And his after receiving his PhD, he obtained a grant from to be a researcher at Dresden, and he became interested in molecular systems, or he started to become more interested also in molecular systems, because before that it was only solids and more physics related. And then after this period, he moved to, well, during his PhD studies in Dresden, he also do exchange programs in Argentina and also in Vancouver at UBC. So he came back to North America for postdoctoral research in Stanford under the supervision of Professor Edward Solomon, who is very well known in bioinorganic chemistry, and later also worked with closely with Uwe Bergman as researchers of SLAC. And finally, he has become a beamline scientist, and now he's helping in the dedicated beamline 15.2, which is dedicated to ultra fast processes in the synchrotron. He also do some work in LCLS, and so welcome. Let's hear what he will talk about today.
Yeah, thanks a lot, buddy. And thanks a lot, Liliana and Niels. Sorry for this wonderful opportunity to talk here, to come to Mexico, have a little school, talk about absorption and emission, and like what we do, how we earn our salaries, and how we help others to, like, excel in their science. And so yeah, I think I have like it's 90 minutes. So the first 45 minutes will be about X-ray absorption spectroscopy, and the second half will be about X-ray emission spectroscopy. And I explain what all of that means. So this is very much like a presentation with where I go in all the details. Will be by far not as entertaining as Christoph's. So don't have your hopes too high. But let's just dive into it. So as a motivation, why would you want to do X-ray spectroscopy? Like in general, when you have like an enzyme, for example, an active site that has an iron or chromium, manganese, whatever, you want to know, like, usually what is like the valence of the transition line, what is the oxidation state, what is the nature of the surrounding ions, how well is the covalent mixing, how does it all work? And there are a bunch of methods that are very, very, very useful and super popular and very, well, not just popular, also very successful. For example, EPR, NMR, UV-Vis, or, magnetization measurements and others. What they all have in common is that they probe the whole molecule usually. Like when you have an EPR signal, you get the signal from the whole molecule. You don't know if there, like when there's no signal, is it iron in the center, for example? Does it have no spin, or is it just antimaterically coupled to some local ligands? And in order to get around that, you can do X-ray absorption spectroscopy, absorption or emission, because it's site selective for the metal. And so that's a little bit the motivation of why we want to do spectroscopy. And for that, as we've just learned, there are X-rays, and there's a bunch of different X-rays if you want. And different means different energy ranges. So they're all photons, so they are all the same in that sense, but some have more, some have less energy. The infrared and UV is like around 1 electron volt. When you then go into the soft X-rays, the soft X-rays are in the range of, let's say, 200 to 2000 electron volts, roughly, more or less. And these are ranges where you find like the KH of like carbon, nitrogen, oxygen, but also the soft X-ray LHS. We will talk about these of the transition metal ions. Then we have the tender X-rays, which are usually defined in between 2 and 5 kilo electron volts. And there you have like the KHs of like calcium, chlorine, sulfur, and the like. I will not deal with these ones here, but the principle are always the same for all of them. And then we have the hard X-rays starting at around 5 keV all the way to, you define it, let's say 30, 40, 50 kilo electron volts. And so the ones that we're interested in mostly, in this presentation at least, in transition metal ions, between like 6.5 to like 9, 10 kilo electron volts. But you also have others like iridium or selenium that are a little bit higher, or platinum, and they're all reachable. So before you learned that there are synchrotrons, and here's like a little map where all the synchrotrons are, and the red dots are light sources, meaning synchrotrons near accelerators. You see that it's pretty much dominated here in the Northern Hemisphere. There's one here in Sao Paulo. I'm not sure of this one here. There's one. There's one in Thailand, exactly. But Thailand should be up here. If this one here is actually already below or above the equator, you realize I don't even know which one it is. And then, of course, here down, there's one in Australia, which is obviously also in the south. Before there was a question, and you asked, like, where is Stanford? Actually, here it is. On the very far west of the US. You notice there are 2 dots. One is Stanford, the other one is Berkeley. They're right next to each other, is like half an hour, 45 minutes to 1.5 hours drive, depending on traffic. And then, well, we are around here. And so where I currently work is at Stanford at the synchrotron. So that, as I said, is up here. And if you have like want to learn a little more, there are here some pages of like an older beamline that describe a little what it does. And as Christoph also already told you, like a synchrotron, the electrons are going around in a circle. They get like kind of refreshed every 5 minutes or so. And so you have a ring with constant electrons, which then, when they go through an insertion device or a bending magnet, then produce photons that we use. Which means you can have a lot of different beamlines. And so at Stanford, we have like around 20 different beamlines. There are bigger ones. It's a small one, as one of the first, as we have learned. There are bigger ones with like even up to like 60 beamlines that can run at the very same time and do experiments at the very same time. And then beamline 15, this is the advanced spectroscopy beamline. That's what I will mostly talk about. But there are also many others, like imaging. So red actually is hard X-ray. So we have imaging beamlines, you have scattering beamlines, you have absorption beamlines. we have a whole bunch of options on the synchrotron. So when you have an experiment that you would like to do, you can go to the website. This is the one for Stanford, for SSRL. But you can also go to many others and just see which beamlines they have, what methods these provide, and what you can do with this. And the methods, let's quickly go over these. Generally, there are like, roughly speaking, 6 methods that you could say. One is like diffraction. There you need a lattice crystal, like a periodic crystal, more or less. And then using Bragg's law, you can find out what is the lattice structure of it. You know, you rotate the crystal in all directions, and then you get a reflection or not, and then you know how it looks like. We won't talk about it here. Then there's X-ray scattering, wide and small X-ray scattering, which basically means you like bounce off from an ion or from an electron cloud in your protein, for example. And then you can have an idea of the rough geometry of the enzyme. So these are methods that deal with the structure exclusively, and I won't go over them here. The other 3 are like absorption, emission, and also photoemission, and they're all strongly like related to each other. An absorption experiment, so you have here, you know, that's kind of like Bohr's model. Here's the nucleus, and here you have the number of electrons around in different shells. There's a photon coming, and it excites an electron from a core level into an unoccupied orbital. And so then the photon is gone, and if you measure the number of photons that come in and you measure those that come out, then you know at which end, you do that for each individual energy, and then you know the absorption spectrum, because it's the absorption of the photon. So that's an absorption process. The other one is an emission process. So again, you have a photon coming, but now you don't excite, maybe a little fast, let me go back. So you excite again an electron, but not into an occupied orbital, but an occupied. And I should have stopped it here, but when you excite this electron out into the vacuum, you're left with a hole here, right? Because the electron is gone. And so that's an excited state. And an ion does not want to stay in excited state. It always wants to be in its lowest energy state. And so it wants to fill this hole. And so it does it mostly from, like it does it from a higher shell, in this case, for example, a 2p shell. It fills it, but we have a conservation of energy. So now we are at a lower energy state, so it needs to radiate a photon with exactly that same energy. The other option is not just to emit a photon, you can also emit an electron through an Auger process, which is usually the higher probability, but harder to detect. And then the photon that gets emitted can be detected with a detector here. Photo emission now is a slightly different process. It's basically the same as the emission, just you detect the outgoing electron. So you come in again with a photon, you excite an electron, and you measure its kinetic energy. So these are basically the 3 different things. The absorption actually is usually or often measured through an emission process. I'll probably talk about it a little bit later, but in the absorption process, see, you have excited well, this is how it started, right? You excite one into a core, into an unoccupied orbital. It will fill the core and then radiate a photon, which is exactly the same as in an emission process, just that you're not resonantly. So here we will focus mostly on absorption and emission. And let me now start with absorption. So as I said, we have various ranges of energy. So for example, when you have 280 electron volts, that's exactly the energy of the core of a carbon ion. So with 280 electron volts, you excite the electron from a 1s shell in carbon into this 2p. If you're at a higher energy, you are up here and you bring it into continuum. So only when you're at 280 or around 280, you excite into 2p. When you have an iron, when you excite from 1s into the first unoccupied orbital with a 3D usually for the K edge, that's at 7,000 electron volts. So it's way higher. It's very different energy. Or you can, for example, excite from a 2p orbital or from a 2s orbital into the 3D, which is around 700 electron volts. So these are very different energies, and they're very specific to each element. And since they're specific to each element, you now can tune to exactly that one. So you get the information from that specific element rather than from everything that's around it, including that ion. Then let's start what's happening. So I want to start with soft X-rays. So let me go back actually. So we deal here with iron. I will not talk much about, or not at all, actually about the carbon carbon ions, but always stay with iron or manganese or the 3D transition metal ions. And let me start with the LH, which is at soft X-rays. Generally speaking, you always have Fermi's golden rule. You have a ground state, which is I, the initial state. You have a final state or number of final states, F, and then you have an operator that couples the two, which is a light operator. And then you have a delta function of the initial state, the final state, and the energy of the incoming photon. And only when the incoming photons is exactly the difference between the two states, you will have an absorption process. Usually there's just one initial state, which is the ground state, but you have many, many different final states because you can excite into various different orbitals potentially. And then you have, so you can expand this operator. I won't do that here, but just to tell you there are certain selection rules. One is that delta L is plus minus 1. Delta L means you excite from a 2p or from a p into a d, right? P has L equals 1, D has L equals 2, delta L equals 1, so that works. We also have delta M, that's like our quantum numbers. They're given as 0 and plus minus 1. But remember, you also have spin orbit coupling. So actually we have a J that couples L and M. And then the actual selection rules are 0 and plus minus 1, but excluding J equals 0 for the ground and the final state. Another option is that you have an electric quadrupole, so delta L equals 0 or plus minus 2. For example, from the 2s, or from, you could excite into the 3D. Here, L equals 0, L equals 2, delta L equals 2. So that's possible through an electric quadrupole. However, it is super weak for soft X-rays. And so for soft X-rays, as a rule of thumb, you can neglect this. So the intensity from here to here, it exists, you can measure it, but usually you don't because it's very, very low in intensity. And you focus on the so-called L2 and L3 edges. And they're called L2 and L3 edges because L, what we just learned, you excite from the second shell. And 2 and 3, well, it's just counting in energy. L1 is the lowest one, that's a 2s. And then you have the 2p, and the 2p has a spin orbit coupling, right? L equals 1, S equals 1/2, so you can couple it to 1/2 and to 3/2. With the 1/2 low in energy, and so then this is the L2 and this is the L3.
Quick question, out of curiosity, I never thought about this for the Sorry, super quick question. Why, I've always been curious, why is it so faint? Is it because you're going way more L's up? Like the S to 3D? Why is it so weak?
Oh, the electric quadrupole?
Yeah.
So the reason for that is the operator here. You can describe it like in a series.
Mhm.
So it's like an e to the power of minus IKR. And so you
so
can
it-
expand it in a series. And the series of e to the minus x is like 1 plus x plus and so on and so forth. And so the first one, the dipole, is where we expand the series as a 1. And the second one is where expanded times like x, and x is k times r. And so when you need to know k and r. When that is way below 1, then you can neglect it. So r is already given by like the size of an iron electron cloud, which is some picometers. And then you need to know k, right? And so k, you know it from the energy. You can convert energy into a wave number, and so then you can just like multiply and see if it's way below or below 1, or if it's not. And so for soft X-rays, it's way below 1. And so
Okay.
for hard X-rays, if we see later on, it is around 1. And so
Okay.
there does play a role.
Thank you.
Yeah, thank you for the question. So I talked about L2 and L3. Now let's look at the spectrum. And so this is one spectrum that I measured some time ago. And so you see 2 different regions, this region here and this region there, at 2 different energies, split by around the like 15 electron volts or so, which is 3.5 times the spin orbit coupling. And so the 2 regions correspond exactly to L equals 2. J equals 1/2, so the L2, which is at higher energies, because it is lower in. So it is at higher absorption energies because it is lower in absolute energies. Because the excitant is 3D, the 3D is always the same energy, and so this energy is larger from the L2. And here this is then the L3 with J equals 3/2. And the intensity ratio of these 2 is roughly 2:1. Because for J equals 1/2, you have M equals plus 1/2, minus 1/2. And for 3/2, you have 3/2, 1/2, minus 1/2, minus 3/2. So you have 4 options, and 2 options gives you a ratio of 2:1. It doesn't hold it exactly because they somewhat interact, but it's roughly 2:1. And then here I have like this gray, which is like a background, because when you absorb, you always have a jump in the signal. All right. So let's see if we can kind of like intuitively think of, can we interpret the spectrum for LHS? And so this example that I've used here is an iron 3 tech-N molecule. It's 5d electrons, so it's ferric, and it's in a low spin. It has a strong Leyden field, and we have it in a low spin configuration, which means the T2G orbitals. Is that clear what T2G and EG refers to? Someone? Yes, no? What T2G and EG refers to, is that clear? That will show up more often. Yeah, it's clear? Someone else?
This pertains to the 5 orbitals, correct?
Yeah.
Yes, and so it depends on basically whether or not you're filling the electron. Oh, no. As far as I understand it, Dr. Kroll, basically depending on how you fill in your electron diagram, especially in a D5, you basically split 2 of the possible orbitals, and so that they're higher energy and cannot be reached in order to not have ambiguity in the system.
Yeah.
Is that full of shit, or?
Yeah, so they're split because of the
polite.
crystal field. Tag N is in a cubic crystal field. It has 6 neighbors. Exactly. And the so-called T2Gs, the lobes look at them directly, and so so it's actually the opposite. For the T2Gs in between, and for the EGs to look at them, that face, and so that's what that higher energies. Exactly. And so the crystal field here is strong, which means it breaks Hund's rule, right? Hund's rule wants all the spins to be parallel so that the electrons are as far away from each other as possible. Here we have a case where the T2G orbitals are all filled besides 1 electron. So when we now think, okay, when we look at our spectrum, here's the L3, here we see 1 feature, and here we see another feature, which is somewhat reproduced here for the L2. Then you could think, okay, that's the T2G, and this is the EG. The splitting between them is what's called T2G, which is the splitting between the orbitals. And then, yeah, as I said, T2G and EG. So that would be like the naive interpretation. Unfortunately, it's not exactly like that. Life would be too simple. And what you find when you look at like the real numbers, and this is not exactly like 10dq, it's somewhat similar. It is obviously related, but it's not exactly. The peak ratio between them here is not 1 to 4, and you wouldn't expect a ratio of 1 to 4 because you can excite 1 time in this one, in this orbital, and 4 times in these. So we'd expect an intensity ratio of 1 to 4, and it's not like that. And the L2 is obviously, it looks quite different. So what to be done? Or why is that? And the reason for that is in the excited state, we have a hole in the 2p orbitals. And the electrons in the 2p and the 3d, they interact strongly. They see each other. There's a Coulomb repulsion and exchange integrals that you have to actually include. So the strong overlap of the wave function, they actually make it complicated. And the complication leads to that you have what's called multiplet effects. So instead of saying, okay, that's excitation T2G and here you have the EGs, if you do simulations, you get a bunch of final states. So the blue lines that I have here, that's a result from a simulation using here a code called CTM for XAS. Tomorrow, Mario will talk a lot more about that and how to use it and how to do a lot more wonderful things with it. And I don't know if he shows this similar spectrum too, but you see here, so you see vertical lines. And so vertical lines mean where the energy is of the vertical line. That's the energy of the final state. And the height of the vertical stick is the intensity at that point. And then in order to get a spectrum, because every hole that's lifetime broadening, you broaden it with the Gaussian and Lorentzian. And then you get a spectrum that looks like the blue one. And with the tons of sticks underneath, you know, okay, you're kind of lost by making exact prediction of your spectrum. And I emphasize exact because you can do a lot of qualitative assignments. And you can do that just partially by looking at the spectra. So you have a bunch of spectra. That's an iron 3 high spin. That's an iron 3 low spin. And that is also an iron 3 low spin. Yeah. And so here we have an iron 2 high spin, and then we have 2 iron 2 low spins. And they all look quite different from each other, which is very nice because it can give you a fingerprint option. So the iron 3 high spin, this feature here is pretty close to this one. And that makes actually sense, because if that is somewhat related to T2 and EG, 10dq needs to be small for high spin, because you obey Hund's rule, and large for low spin. And that's what we see. The 2 low spin ones, they're more separated, which is very nice. When we go to a iron 2 low spin or a high spin, they look somewhat similar. So there it's not necessarily so easy to distinguish these two. But you can actually, you can also use the ratio of the intensity of the L2. And what's also interesting, when you look here at iron 2 hexacyanide, you see additional feature here, which is pretty strong. I will say a little more about that later on, I believe. But this feature here comes from a back bonding. So you can have a donation from the ligand to the metal, and you can have pi back bonding usually from the metal to the ligand. And so the cyanide has strong pi back bonding just because of an MO diagram where the orbitals are. There's big overlap, and so they can go back. And that is like very strongly visible. So we have that information also in the spectrum. So we get information from oxidation, geometry more like from simulations, the spin states, and partially covalency. Like when you compare these, this is high, this is low, it gives an idea about covalent mixing. I come to that in a few slides. Another important factor is that's the intensity. Like when you take the spectrum and you just integrate, you get a number. you get the intensity, the total intensity of the spectrum. And the total intensity actually turns out is proportional to the metal character, or effectively the number of electrons. So you could imagine, if we go back here to our example here, you integrate this one and you get a number that you call 5. That's it. Now, when you go to a D6 system, you fill this one here, and so the intensity is lower. You can call it, let's say, 4. Now, when you have covalent mixing, you have electron density also on the EG on the T2G. So the metal character here will increase. Like you can imagine that you have kind of effectively another electron here, seeing they're just coming from ligand to metal charge transfer. So you have more metal character for the electrons, or less for the unoccupied, because you're always excited and unoccupied. So the intensity comes from how much space you have. And so then with the more ligand mixing you have, the lower the intensity. And it turns out that that's actually linear, pretty much. So here on the bottom, I have the effective number of holes. And here I have the total LH intensity, so the integration of it. And it looks pretty linear, which also means that if you have a system and you don't exactly know what it is, you can get the total intensity and then see where it is on that line, and then compare, okay, it's more or less covalent to like a reference that you have. So that's like a qualitative option. Now, another qualitative option, since we talked about orbitals, and we talked about here for this feature here in the low spin. So that's a spectrum of an iron 3 low spin. Let's probably even take N again. Initially, I said, okay, that could be the excitation to the T2G orbitals, and that could be into the EG orbitals. Now, with the multiplet codes that I just talked about, you can also use it and figure out what is the character of the transition that you do. Meaning, in what type of orbitals are you actually exciting into? And that is shown here. Gray is into like pi orbitals, meaning T2G in this case, and black means sigma orbitals, so the EG orbitals. And turns out that at the L3 edge, the first feature here is 100% pi character. And the higher energy feature is pretty much a mixture of the two. So that's why the ratio of this feature to this total one was not 1 to 4, because this feature contains both pi and sigma character. But when you compare the total amount of pi and sigma character, it's still 1 to 4, if you have an ionic system. And it's more complicated, but similar for the high spin case. That's an iron 3 high spin case. Here you have this feature that you would call T2G, but now it's more of a mixture. It still has more pi's and sigma character, but it's more of a mixture, whereas this one here has a lot more of a sigma character. So even though it is somewhat like unclear how much you really have in there, you still know that for D5 low spin, the first feature is purely pi character. This one here has a lot of sigma character. And for the high spin case, this one has more pi's and sigma, and this has more sigma. So there, when you look at two spectra and you want to compare, you can get an idea already, like to totally qualitatively. And so here I use the example of iron 3 TechN and TPP bisimidazole. So that's this here is a porphyrin with 2 imidazoles as actual ligands, which is a relatively highly covalent system. And here we compare the LHs to each other. And the first thing you see when you just look at this feature here, so we know this one comes from pi character almost exclusively. We see that the intensity goes down for TPP bisimidazole, and then also shifts a little bit closer to the main peak here, or not main peak, to the stronger peak. And that can already tell us two things. The reduction in intensity here means it is more covalent because there are less holes available effectively as we can excite into. And the shift, or that these two features are closer together, means that relatively speaking, 10dq is smaller. And that's actually exactly what it is. So when you do like DFT and you compare these two, then you find that they have clearly a more covalent pi character, but a somewhat similar sigma character. So that's a result from a DFT calculation. And you get that here just by looking at it. Okay, this one equals down, and this is somewhat similar. So you can already qualitatively have that idea about the system, even without doing any expensive simulations. There are also more, more things that you can do qualitatively. One is the effect of the oxidation state. So now let's compare iron 2 tag N with iron 3 tag N. So the iron 3, it has a hole here in the T2G, which is this feature again. For the EGs, they're very similar. And so these are the features that originate from excitation in the EG orbitals mostly. And you see that there's a shift in energy between the two, with the ferrous case being lower in energy than the ferric case. And so why is that? And the reason for that is like in the screening of the core hole. Remember, you excite, in this case, a 2p electron into a 3D, which means you're left with a hole in the 2p. And so that gets seen by the core, which is positively charged. And so when you have more electron density in the 3D orbitals, this electron density screens the core. And so it pulls everything down in a different way. And so the more electrons you have, the more it's pulled, the more it's screening. And so the lower it is in energy. And so when you see something where you know, okay, that's pretty much the same spin, I know that one is at higher energy, the other one lower energy, you can in principle say it will shift to higher energies when it's oxidized, or it goes to lower energies when it's reduced. That's kind of like a rule of thumb that you have to be careful with, though, as you see in this slide here. This slide here, now we go away from iron, we go to a copper slide. Copper slide. Copper is like super nice because it's very simple. You have so instead of having here, you know, like 5 holes or 4 holes, when you go to copper 1, you have no hole. That's the easiest of all because you don't get any intensity, because you have nothing you can excite into, which also means it's not very interesting. When you have a copper 2+, then you have 1 hole. And that is relatively easy to interpret because you don't really have all these multiplets, because there's only one state that you can excite into. And so these are 2 spectra. One is copper chloride in D4H symmetry, shown here in this dashed line. This one is taken, I mean, you see it's like, I don't know, from the early 90s, I believe, early experiments. And here you have plastocyanine, which is an enzyme, I believe. And you see 2 things between the 2 of them. One is plastocyanine is way lower in intensity, right? And so that is the same argument as that I brought before when we look at the T2G peak between iron tag N and iron TPP bismuthazole. It went down in intensity because it's more covalent. And that's exactly the same here for copper. So plastocyanine has 41% metal character, copper chloride 61, and so it is higher in intensity. However, you still see an energy shift between the 2, but they're both copper 2+. So they both have the same oxidation state. And if you remember what I said before, okay, you shift to higher energies when you're more oxidized. No, they're not more oxidized. They're the same oxidation state, but they have a different crystal field. And I can imagine, you see it here. These are the diagrams. The 2p is, let's say, at the same energy. And then the 3D manifold is split differently by the crystal field, right? And you excite, so they both, the 3Ds again, are pretty much at the same energy. And now the uppermost orbital in energy is the one you excite into, because that is the one that has a hole. Now, if your crystal field is larger, this will be at a higher energy. So absorption energy will be larger. So you can also see a shift by a larger crystal field, which means you do have to be a little careful when you see, okay, I see a little bit of it goes to higher energies. It could just be because you have a larger crystal field, but still the same oxidation state. And finally, what I want to say is that's like an advertisement slide for Mario tomorrow. When you do the simulations, you can not just find that you get your spectrum, and you can say, okay, it fits to, let's say, an iron 3 low spin, or it fits to an iron 2 high spin. You can also get information out about the covalent mixing, even something that's called differential orbital covalency, meaning that you get the amount of covalent mixing for different orbitals. Because the mixing for the EG orbital is different than the TTG orbitals because of different overlap. And so when you do these calculations and to list tomorrow's talk tomorrow, then you will know how you can analyze your data in a lot more detail. Which, by the way, is this is now a real physical meaning. Because that is something that you can also compare to like DFT calculation that you've done. So by there you have an option to couple these two and say, okay, it all matches together. I believe the DFT, and now I can go on and do whatever I want to learn from it. So these are soft X-rays. To quickly summarize, we have sharp features and nice spectra, as you have seen. They're site selective because we have a core electron that's involved. The sensitive oxidation spin and to the geometry. And last slide, the differential covalency is actually accessible through simulations of the spectrum. So if you don't want to do soft X-rays, or let's put it the other way around, why wouldn't you want to do soft X-rays? I mean, you saw it's all these nice features, and they come, of course, it comes with a price that you have so many features. One is, or the main one is that it's 700 electron volts, which means that the photons get absorbed quickly by air, for example. Like in water, it's like a micrometer, roughly. That's not really much. Usually often samples are bigger. In air, it's like a millimeter. If you have a solid, like R2O3, it's like a micrometer. And so that's difficult. They're difficult conditions, which means you want to have your system in a vacuum so that the photons don't get absorbed even before you reach your sample. So that makes it sometimes challenging. The option out of that is you just increase the energy of your photon. The higher the energy of the photon, the more or the less it gets absorbed. So now when you go in air, we are in the meter range at 7,000 electron volts. In water, it's like the millimeter range, and you even have 10 like micrometers in like a full solid. So you don't need vacuum. The environment is way easier. You can use different systems. We can put a cryostat and cool sample. That's easy. You can do like catalysis experiments, do in situ experiments, or you can use the liquids. You have a lot more options. And so that's why hard X-rays are interesting. It's 7,000 electron volts is, by the way, roughly the absorption energy of iron. Now, a big difference between the two is how long these core holes live. So what you saw before for iron here, oh yeah.
How much
Yeah. So that depends pretty much on the experiments. When you detect photons, you can get away with like 10 to the -6 millibar, or torr. I don't know which one. They're similar, millibar and torr. When you want to detect the outgoing electron, you're better off with the high vacuum, like ultra high vacuums, like 10 to -8, 9. And then depending on the accuracy needs, like between, let's say between 10 to the minus 6 and 10 to the minus 10.
Thank you.
Yeah, thank you. Okay. All right. Let's come back to iron for the LH that we just looked at. The broadening, the lifetime broadening is like 0.4 electron volts. While when you look at the KH, it's broad. It's 1.3 electron volts, around 3 times more. And the reason for that is simply like the options, how quickly you can fill the hole. Right? When you have one S hole, you can fill the one S hole from the 2p's. You can from second shell, from the third shell. You have a lot more options than for the 2p's, which can only be filled from the from the third shell, basically. Which means they live longer. And when they live longer, since you know about Heisenberg and his uncertain principle, that delta E times delta T must be lower or equal than pi star divided H bar divided by 2. You can couple them, and then you get, if the lifetime is shorter, you get a broader energy resolution. And so that's why the iron KH is around 4 times broader. And that has serious consequences, as you will see, because it will smear out all the features, pretty much. So, but first, let's go back to Fermi's golden rule. Same slide as what I had before, but now instead of exciting from the 2p into 3D, we have a 1s into the 3D, or potentially in the 4p. So 1s into 3D, that's electric quadrupole allowed. So delta L plus minus 2. And so now, since the energy is higher in the expansion that I mentioned before, K times R is around 1, or sufficiently close to 1 so they cannot neglect it. We can, with delta L equals 1, S goes into P. So where's the next P? Here it's a 3p that's fully occupied, right? So we cannot excite into that one, but we have the 4p. So one can excite with a dipole into the 4p. And what one has to remember or to know, I didn't write it here, but the dipole transitions are around like 50 times or 100 times stronger than a quadrupole transition. So this is way more effective than this, but still it's very visible, as we see here. So that's generally like in hard X-ray absorption experiment, how like a typical spectrum could look like. This again is iron hexacyanide. Here, down here, the little feature there, these are the excitation into the 3D orbitals. This here is excitation into the 4p. And then this here are excitation into the vacuum, and then that's the excited region. But Niels, I believe, will talk about, I don't know, in an hour or so, or after lunch. And actually, I'm showing you 2 different spectra. One is hexacyanide, that's blue, and one in red, that I forgot what it is. It's a different one, it's also iron. Important is it's different, and you see that here the shape, the exit actually goes all the way further. It looks different. Here is the Xane's region, or the shape resonance, which is due to excitation of 4p, which also looks different. You get electronic and geometric structure from that. I believe Mari will say more about it on Wednesday. And here's the pre-etch region. So I will not say anything about this one here. That's all Niels' territory. I will talk a little bit about this and a lot about this. So first, we are, that's quite an, oh, I forgot that I had it like this. So explain again what the pre-etch is and what the main etch is. So the pre-etch is excitation into the 3D orbitals. So it's down here, it's quadrupole. mostly quadrupole and very weak in intensity. And you excite into the 4p orbitals, which is the edge region here, which is very strong in intensity. And then when you into the continuum, you go up here. That's repetition of what I just said previously. There are a number of ways to look at your data. One is a qualitative way of looking at it, and that's what I will go over mostly here. Basically use it as fingerprints, or you compare to model complexes, or you just like think about a little bit how it should look like, and then try to analyze the data. But you also have many other options that you can use, like band structure that gives you density of states, which will help you. You have a multiple scattering approach, PEF, you just learned in the previous one, and you learn about more later on with Niels, or you can have a multi-orbit approach, which you can use. The multi-orbit will actually fail when like going for the rising edge and above, but it will be very good for the pre-edge. So let's start with that again, kind of with the same thing that we ended with the soft X-rays, oxidation state. They're explained when you go from a high oxidation state to a low oxidation state, it will go to lower energies, and that's because of the screening of the core hole. That argument holds exactly the same for hard X-rays. And again, you see the same time. You go from copper 2 to copper 3, you go higher in energy, or when you reduce, you go lower. And that's an important consideration. You have like similar ligand systems. It's also true on the right when you go for nickel, but the effect is smaller. So it's not just that you say, okay, I have a shift, so it is that amount that it needs to change from oxidation. Now I go to another complex, and it needs to be exactly the same. So nickel is somewhat insensitive here for the two complexes. And so just because you only see a small change doesn't necessarily mean that there's hardly any change in oxidation state. So there one has to be a little careful. Before I also mentioned your crystal field can change. Now here we have another example. These are both Rn2 complexes, and the rising edge is very different in energy. For the pre-edge before, for the LH we learned it could also be the crystal field, but the crystal field is not so much for the rising edge. But as it turns out, these are two different spin states. One's a high spin, and the other one's a low spin. And the difference between the two is that for the high spin, the electrons are very nicely separated from each other. They have like a sphere. And so they work very well for screening the core hole. When you have a low spin, so they're all the T2G, they're all kind of clustered together. And that doesn't work well for screening. And hence, you have different energies. You're at higher energy when you're for a low spin, and at lower energy when you're high spin, because it's a more spherical way of where the electrons are actually located. So that is one thing to keep in mind, which can help you then to. Yeah,
Because I will have thought so low spin is higher energy because your empty, what are the EG orbitals, assuming these are the orbitals, are higher energy, so the holes you're excited into are higher energy.
Yeah,
that's how I would have
thought
about it.
That's a very good point, and I will come to that later because it's very, very valid, and it's valid here in the pre-edge
for the
3D, while the 4P don't get split that much by it, because the 4P don't directly participate in bonding. And so this CR excitation is in the 4P. And so that's why the splitting of the EG and T2G does not matter much for the 4P orbitals. But for the EG orbit, sorry, for the, what I'm talking about, for the 3D orbitals, there it matters a lot.
So how can we simply understand this shift for the 4P? Yeah, what do you mean by the spherical?
So now, we excite still into the 4P, but what gets screened is your core. right? You have the positive charges in the core, and they get screened by all of the electrons that are in the system, in particular also by the 3Ds. And so when we have a high spin, the 3Ds are more kind of like spherical. If you think about it like D5 high spin, that's actually they're as far away from each other as possible, follow Hund's rule, and it's a spherical. And so that acts very well for screening. But when they're in the low spin and they're in the T2G orbitals, then the screening of them is less effective because they're just clustered together. Yeah, the screen. Yeah, exactly. And so it's a shielding of the core. And then, but you excite it for p orbitals. So I realize it's a little difficult to wrap your head around.
You can draw it on a napkin over a beer.
I can do that.
We haven't couple policy yet in the staff, so maybe after we exit the campus, please.
Later. So speaking of 4P and the shape resonance, it also depends on what kind of ligands you have. And here I give the example of a copper system that has like 2 ligands. So you have like a linear orientation. You have 3 ligands, which is in more like in plane. And then you have 4 ligands in a pretty symmetrical way. And so even though I said the effects of the crystal field is not that strong on the 4P, it's still there. But they do not participate in bonding. And so when you have a linear arrangement, then you split the PZ orbitals from the PX and PY orbitals, with PX and Y being lower in energy because this here is the Z-axis. And what it leads to is you have a strong feature here and like a weaker feature here on the shoulder, which is excitation in X, Y, and then into the Z. When you go into a situation where you have 3 ligands, like this, you have the PX now split from the PX and Y, but they're closer to each other. And so now you see actually weaker intensity and more distribution of energy. And then when they are symmetric, they're higher in energy. This is now the red one. And you see like a somewhat featureless spectrum. So that part here is called the shape resonance. And as you see, it's very sensitive to the structure around it. So you have excess, where you can get it from. You also have the shape resonance that is sensitive to your structure around your transition metal ion. And I'm very much looking forward to Mario's Wednesday talk, talking about. And so the shape resonance, how effective it is, I want to illustrate here an experiment that we have done some years ago. This is actually a pump probe experiment. This is cytochrome C. The cytochrome C, when you pump it with an optical laser, so cytochrome C is it's a porphyrin with an iron in the middle. It has an imidazole as one of the X ligands and the 3 ether on the other one, so it has a sulfur. When you pump it with an optical pump, that sulfur bond kind of breaks and it goes out, or it leaves the iron. So you go from a 6-coordinate system into a 5-coordinated system for a certain amount of time. And so it's shown here. So that is the ground state, how it looks like. And when you measure the KH, the iron KH, this is in orange. That's how the spectra look like. It was taken at a linear accelerator, so that's why it's relatively noisy. And you can simulate it using multiple scattering codes. This is due MXAN, that is from the Italian group that Christoph was talking about. Now, when you excite the molecule, then here the Savisa goes up. It increases. Like the distance goes from 2.29 angstrom to like 3 angstroms. And you see a clear change here in the shape resonance. And so you can use multiple scattering, and then you can get the structure. And you see that that works pretty well, which is then an evidence that actually what happens at the theresa does go away for a certain amount of time when you're excited with an optical laser. And so that's an example where you clearly see from a 5 coordinate, this is quasi 5 coordinate, because 3 angstrom is pretty far away, to a 6 coordinate, and then the change here in the shape resonance. So now let's go away from the shape resonance and come to the pre-edge, which is excitation mostly into the 3D orbitals. So that's shown here. So in the pre-edge, so the ground state is 1s2. You have 6 p electrons. You always have 6 p electrons, and then n electrons, for example, in the 3D. And then your excited state, you have a whole 1s, an additional electron in the 3D shell. The nice thing is, the very nice thing is that the 1s does not interact much with the 3D orbitals, which is completely different to the LH before. For the LH, you had a huge overlap of the wave function with the p and the d. Here, it's very weak, 2 orders of magnitude less weak, and in first order, you can neglect it. Another thing is the 1s orbital has A1G symmetry, so that doesn't disturb anything either. So we can actually just think of the 3D n plus 1. So we forget about that there's a 1s core hole and just think about the 3D orbitals, which means we can Tanabe-Zagano diagrams for like a quantitative analysis. So let's do that here. So Tanabe-Zagano diagram means it gives you here an energy for the various states that are present for different crystal fields, basically. And so here I have the example of an D7. And I use D7 because I want to use a D6 system as a ground state. So I use the Ferris low spin complex. So all the T2G orbitals are fully occupied, and only the EG orbitals are empty. And so in the final state, when we excite from 1s in the 3D, now we have 7 of them here, which means we need to look at Tanabe diagram of D7. Even though the ground state is D6, final state is D7. Okay, what does it tell us? We think a little bit about the group theory that we had, and we know that the ground state, the orbital ground state, has A1G symmetry, is completely symmetric, and the spin is 0, which means it has multiplicity of 1. So we have an A1G1 ground state. Now, we excite from 1s in the 3D, so it's a quadrupole operator, delta L equals 2. And the symmetry for these are T2G and EG. The T2Gs are all occupied. We can excite from them, so only we have the EG left, which means the final state is an A1G cross an EG, because that's our excitation, equals EG. And we know now that we have a spin of 1/2. So it's multiplicity of 2. So we know that we have a final state of EG doublet. Does it make sense? And then all we do is, let's look into Tanabe-Zagano diagram, where we find E2 states. So we have to look at this side of the diagram because we are in a low spin system. And turns out, so here's one, it's the lowest energy, and then none of the others fulfill our conditions, which means there's only one transition that we can do. So that tells you a spectrum of the pre-edge is like 1 peak. There's nothing else but 1 peak. And when you do the experiment, and they have done that here, that's a paper from '93. It's kind of hard to see here, but here it's better. It's just one feature underneath, and this is this one transition coming from a quadrupole. It gets a little more complicated when we go to a high spin case. So same Tanabe-Zagano diagram, but now we're in the high spin, so we are looking at this half of the diagram. So okay, we have 6 electrons that we need to like place into the 3D orbitals. 5 of them will all be high spin, let's say, and 1 is low spin here in the T2G, which means that the orbital symmetry is T2G, and we have this S equals 2, so it's spin multiplicator of 5, so we have a quintet T2G. in the final state, we have D7. And so what kind of symmetries can we reach? So we can excite with a T2G operator into the T2 orbitals and the EG operator into the EG orbitals. So now we need to do the mass T2G as a ground state cross the EG for this one, or cross EG for to go to the higher ones, and T2G to go into the pi orbitals. And when you do your mass, you find that you can reach T1G and T2G symmetries. And we also know that at the end we will have S equals 3/2, so we have a quartet. And so that leads only for these two options, quartet T1G and quartet T2G. And then again, you go to Tanabas-Gano and search, okay, where do we have them here? So one is here, that's the lowest. We find one here, that's a quartet T2, and we find another one here, which is quartet T1. And all the other ones do not fulfill the condition because they either don't have the right spin or the right symmetry. So that tells us we must have 1, 2, 3 features in our spectrum at different energies. And now let's look at the experiment. It's shown here. This is the K edge. You subtract the background, then you get it out a little better. And indeed, it turns out that there are 3 features underneath, which come from the ones that I just mentioned. And how far away they are from each other, and energy now depends on the crystal field, which means it depends on where you are here in your Tanabas-Gano diagram. Which means for quadrupole transition and K edges, and you look at the pre-edge, you have a very nice way of interpreting what kind of spectrum you have, just by using Tanabas-Gano diagrams, which is actually a pretty nice way of looking at things and understanding why a spectrum looks the way it does. And you can do that because, remember, the 1s interaction with 3D orbitals is very weak. 2p is strong, 1s is weak. So now let's do the same what we did for the LHS and for the rising edge. Yeah.
Hello, me again.
Yeah.
Is this generalizable to non-inorganic complexes? Does it look the same, for example? I mean, obviously I have experience with bioXAS and I've seen some pre-edges and stuff, but just would it be like on that previous slide, would you be able to do the same thing for a protein system that had an iron in a high spin or low spin?
Yeah.
It's completely generalizable.
Yeah, it's completely
so powerful.
Yeah, it's completely generalizable because all that matters is your iron.
Mm-hmm.
You see the iron and how the iron, so you see only the iron, but you also see what the iron sees.
Well, right. So I'm thinking about sort of distortion of sort of a typical setup. Would it be reflected in there? Like, how generally in nature things are kind of skewed from the typical, I can't think of the word, jet lag, but symmetry.
Yeah. Yes, very good question. So Tanabas-Gano diagrams are OH symmetry, basically.
Okay.
They're a cubic symmetry. When you have I have 25 minutes for what? The whole thing?
I would want to go to the side of this.
All right, I still have the emission part, which is more than 25 minutes. Am I so far behind? I'll try to be a little faster later on, but still clear. So you don't have that much food later on than during lunch, right? If I continue like that. So yeah, the question is very good. So this is for first of all, you need I'll tell later, you need inversion symmetry so that you're only looking at the quadrupole part. And if you have a D4H system, then this description here doesn't hold anymore because you split your orbitals. So it's for cubic systems.
Okay.
So there it's very, very nice. You can do the same thing, like similar things for D4H. It's just like the next step from it.
Okay.
But the nice thing is 1s also there doesn't play a role.
Just a comment for Kelly, because in proteins things are not perfectly
Right,
cubic symmetry, but still it works really well. Like you say, okay, if it were cubic, this is what you will expect, and then you distort from there,
Yeah.
and it works.
Cool.
Yeah, the nice thing is that the X-rays, even though I say like inversion symmetry, for example, you must not take it literally, because the X-rays don't do either. First of all, when I talk about its local geometry, about what you excite, and then when you look at the cytochrome C here, you have the 4 iron nitrogens in the plane of the porphyrin. You have one below, and then here you have the sulfur. I mean, that's not really centrosymmetric, right? But the iron, for the iron's enough. It's enough centrosymmetric, and so you will only see here quadruple transitions. So it's quite powerful in that way, and it's not that dramatically sensitive to it. So then quickly for the pre-Hs, this is basically the same as what we had for the LHs. First of all, you see that's a change in spin state, and you see the spectra look very different from each other. And that is the example I gave you before. 1 feature here and 1, 2, 3 features for the high spin. And then iron low spin, again, you see the change here at the rising edge, but also you see a change. So both the low spin here are in iron 2 and iron 3. You see a change in the oxidation state. And then here, this is a lot closer actually to an actual crystal field, way more than for LHs. And then as the last slide, to make it a little more complicated, that's to your distorted enzymes. In the moment when we lose the inversion symmetry, we don't have gerade and ungerade anymore in group symmetry. When you don't have gerade and ungerade, you only have like A1 and T2 orbitals, for example. And so when you think about something in, let's say, C4V symmetry, so the Z squared orbital has A1 symmetry. The PZ orbital also has A1 symmetry. Let's say, or let's take a step back. Let's say you're in D4H, so which has an inversion symmetry. Then the Z orbital has A1G and the PZ has A1U. So they cannot mix because one's gerade, the other's ungerade. When you take away the inversion symmetry, you go to, let's say, C4V, then you have 2 times A1. And so they can mix, which means you can have 4p character in the 3D orbitals. And I said that's a dipole, which into the 4p is like 100 times stronger. So a little bit of 4p character in the 3D orbitals can make your intensity large. And that's what we have here in this example. This here is an iron 2 high spin, I guess. And now we have a distorted one where 4p can mix here, so the ligand, and the intensity shoots up. And here you see, before it was very small, and now it's like significant intensity. Which is then also like sensitive to local environment. Yeah, so here, very quick summary. You learn basically the same thing from the hard X-rays, with some nice things as we solved it, that the so 1s doesn't really play a role so much, and you can more directly interpret your data. And for those that are more interested, there are a bunch of articles you can read. Many of them are like review articles. That's a good one. That's, of course, is a very good one. So now I have only 20 minutes left.
Skip a little bit of lunch. We are a little bit technical, but I want to do.
Yeah.
I want to be the German to do.
We should take questions. No?
Yeah. How do I switch to the next presentation then?
Not a microphone question, but those slides were so important. Do you think you could share those privately with any of the students here?
Sure, sure. I think I need to stop sharing, but I don't want to stop sharing just like that, so that it doesn't. I'm not sure what stopping sharing does to the recording. Yeah, so now the second PowerPoint.
Yeah. Okay. Thanks a lot for the great talk. And I have a little question that is it possible to study systems with 2 or more metals in a protein with this technique?
Yes.
Yes.
Thanks.
It's very well possible. It's also a very good question. What I haven't like emphasized so far is what you get. It's an average of all iron, for example, in the beam size. Right? You have your sample, and then the beam size is kind of smaller, but it's still like in our beamline. It's like, let's say 100 by 400 microns. So within that range area, there are a number of iron ions in it, and you excite, let's say, all of them. And so you will get an average of all the iron ions that excited, which means if, let's say, you have two sites, one's a high spin, the other one's a low spin, you will see a mixture of high spin and low spin. If one of them is iron 2, the other one's iron 3, you see a mixture of iron 2 and iron 3. And then you need to figure a way where you, like you take, for example, like a reference for an iron 2, and you take a reference for iron 3, and then you see if you can do a linear combination between the two and get your spectrum, which is a linear combination of the two.
It's a little more.
Here's the emission.
Thanks a lot.
Yeah.
Any more questions?
Thank you so much. My question is the opposite of his question. Is possible measure other kind of transitions? I mean, will be possible measure intercrossing systems transition?
Intercrossing between.
Is no is a no metal transition.
A no metal transition? Yeah, so even though I talked about iron and copper, but you can basically measure all elements. So it can be manganese, cobalt, it can be whatever, platinum or iron, iridium. When you think about like carbon, for example, or nitrogen, for these you need, you can measure it, no problem. For that you need soft X-rays, because there, when you excite from 1s into 2p, you're at 530 for oxygen. So there you need soft X-rays. But it all works the same way.
Thank you.
More questions?
Hello, nice talk. So I have a question about, as you said, we can study, for example, iron interaction with a protein or something, or a system like that, but we can study cobalt, for example, interacting with a polymer. Using, for example, a compound as spinels or type spinels with polymer, and studying iron or cobalt as a metal complex in the center. We can know, or we can learn about the oxidation state, for example, or the covalent, but which of the two metals we have to study about? The two at the same time, or using only iron or cobalt?
You can have both in your system.
Yeah.
You cannot measure them at the same time because they have different absorption energies. Like when for iron, it's at 7,130, while for cobalt it's what is cobalt? 7,800, I believe, something like that. So you need to go higher in energy. So when you're at the iron edge, you do not excite the cobalt. When you're at the cobalt edge, or when you have incoming photons that in resonance with the cobalt edge, some of them, of course, see the iron, and they will excite an iron electron into the vacuum, and then you have an emission process that follows from that. What you can do is you can measure sequentially, right? You first measure your iron scan, and then you measure your cobalt scan. And so that you can do that during the same beam time, for example. So you can measure them during the same beam time, but not at the same time. You're not exactly the same time. But sequentially you can do that, yeah.
Okay.
Actually, you can do it with emission, though.
Exactly. Perfect.
Perfect. Yeah,
Yeah.
very good. Very good. What you can do, you can excite both non-resonantly, and then they emit at the same time. It's not an absorption experiment anymore. It's an emission experiment. And I tell you here in the next 45 minutes, I believe. I also thought 45 minutes for the previous one, honestly. Like what you can learn about these. Also, you learn about the 3D electrons and orbitals.
Yeah. Hi, Thomas. I have a question too. We have seen like examples when you have reference compounds, so you can compare the oxidation state, the geometry. But in the case when you have a compound or a sample, when you have no idea about the geometry, or maybe you can have a clue, but in the cases when you have no reference compounds, what is the best? What is the best approach to start to analyze the spectrum?
So if you have absolutely no clue, you're not in a good shape. What for absorption experiments, what is true, as for most other experiments, when you have a series, you win, or you have good chances, let's say. When you have like one single complex with no comparison to anything else, you're in a better shape, worse shape. And so the way you would go about it, if you say, okay, I don't know if it is iron 2 or iron 3, if you stay in the iron. But you know, for example, it is not iron 4, right? And also know it's not like iron 6. So you have already a clue usually about your sample. You also have a clue. I mean, you don't find it on the street and bring it to a synchrotron. You have an idea what is, you could do that though. You have an idea roughly what it is. You might not know if it's 5C or if it's 6 coordinate or maybe even a 4 coordinate. But you have like a rough idea usually. And you know, okay, maybe some of my ligands are like nitrogen, others are something else. And so then from that, you can already start and have reference complexes, because you can just take like an iron 2 low spin complex as a reference, or iron 3 high spin, right? You just take like, you use the library and say, okay, it looks, qualitatively speaking, it looks pretty close to that one. And so then your first guess is, it is, you know, it looks like this, so I claim for the moment it is like that. And then you start to dig deeper. Like, you know, you can do like some like DFT calculations, and with like TDFT, partially you can calculate these pre-etches, and then you can see if that actually works. And so there is a way by having a library to narrow it down to something that actually makes sense. And in most cases, you don't know exactly, is it iron 2 plus or iron 3 plus? I mean, the whole full professors, they're all there. Curious, is it 5C or 6C effectively? Because in many biological systems, you don't know how much something is bound really. And does it more appear like a 5C or 6C? And so that's important questions that are usually not known, or often not known.
Hello, and thanks for the presentation. It was really informative. And my question is, what are the selection rules that make like one transition more intense than other transitions?
You mean why is dipole more intense?
For a quadrupole transition and a dipole?
Yeah, that's like just think about the expansion. You basically have one of first order. Like you can kind of treat it as a perturbation. And that already tells you that one is more, well, what you can treat as perturbation is then less intense. That's kind of the short answer. It's a very good one. I don't have a super good answer.
Okay.
My answer isn't as good as the question, but it comes basically from the expansion of the series.
Okay, thank you.
Maybe we continue now with the emission part.
Yeah. Same title. So when we do not an absorption experiment, but an emission experiment, and let's start with non-resonant case. And then we excite an electron from the 1s. And now we only stay in the hard X-rays. From 1s into the continuum. So we bring it out. We have a photoelectron up here. But we don't care about the photoelectron. We only care about how this 1s hole gets filled. And you basically have three main options. One can be filled from a 2p or from a 3p. And so p to s, that's dipole, so that's most likely to happen. Or it can also happen from the valence into the 1s. That's not a dipole anymore, and it will be very weak in intensity. And they have different names. This is called K alpha, K beta, and K beta valence to core. And here, like some examples, they look very different. I'll talk in way more detail later on about them and why they look the way they look like. So, as I say, we get a spectrum here. So we want to know how the spectrum looks like. And then the question is, how do you measure a spectrum? So I never mentioned it, but for the absorption experiment, just put a detector there and you basically collect everything that's, not everything, but most that gets emitted in photons. Here, we want to scan through. We want to know how the whole spectra look like. And so we need a spectrometer. And the spectrometer works in the following way. First, and that's also true for absorption, you need a defined, or you want a defined incoming energy. And so that's done with a monochromator. We come in here, you hit a crystal, it gets reflected or not, and then into a second one, and then out here. And that is all with Bragg's law. In the next slide, I explain what it is. So we have a monochromator that selects the incoming energy, which is super important for absorption energies, because you want to have a clearly defined incoming energy so that you can distinguish between the orbitals. And then we also need to scan the same thing of the emitted photons. And so here's a scan. The photons come probably from you. They hit the sample, which is here. It radiates everywhere. And then here we have some analyzer crystals that reflect it back into a point where we then put the detector and then we measure the signal. And so the way these analyzer crystals work, same as the monochromator, is Bragg's law. You have a single crystal, silicon often, or germanium, which means you have defined layers. And so then when you have incoming photons, one gets reflected from or diffracted from one layer and the other one from the other. We need to have a different path in between them. And you compare that then to the wavelengths, and then that gives a constructor for deconstructive interference, which means you have a signal or no signal. And so it all depends on the angle here, which means the analyzer crystal, this is a so-called Johann geometry. We're on a Roland circle. And so the sample here is fixed. You cannot move the sample. The sample is where the sample is. And then you change the angle by changing the whole spectrometer. Like you move it like slightly. So when this one is further down, it's a different angle, right? A different angle means a different energy. So by scanning through, you can select different energies of the emitted photons. And then we have at our beamline, we have like a spectrometer with like 7 of these crystal analyzers so that we capture most of the solid angle as much as possible. So that's again how they hit them. And then that is from the top, that's how our beamline roughly looks like. Looks maybe a little complicated. Here's incoming beam, here's a sample, and then it radiates into our 7-element spectrometer, and then it gets reflected back underneath the sample into the detector. We also have some other spectrometer there for Raman, where I don't want to say too much about it, but just want to mention it in the next slide. So since I said, oops, here you need to change the angle in order to get different energies. And the energy depends on the difference between different layers. You cannot use like one crystal and rotate it the way you want it and then get all the energies. That would be wonderful, but it doesn't work like this. With each cut of a crystal, you have only a given energy range, which means in order to select, so to have a huge range of energies that you can cover, you need various cuts and various crystals. So we need a crystal bank, and actually we have that. And so this here is an incomplete figure of all the crystals we have. So here are the different crystals, germanium and silicon. We have some more with different cuts of them, meaning the d-spacing is different. And they cover different ranges in energy, which fit to different elements. So for example, here you have iron K alpha. You would use the germanium, actually it's a 440 reflection, and none of the others really match. And then when you want to use, let's say, iron K beta, you can't use that crystal anymore. But here, that's a germanium 620. So for the experiment you want to do, you select, you analyze the crystals, and then you can measure it. Meaning, if you want to do the experiment where you have like 2 elements in it, you divide the 7 crystals in, let's say, 4 and 3. And if you use, let's say, iron, you measure the iron K beta emission, you use, let's say, 3 germanium 620. Then the other one was cobalt. Where do we have cobalt here? Not here, cobalt K beta. Then you would use a germanium. I think it's actually a 333 cut. So you would just like use different sets of crystals. And what Mario also mentioned before in our beamline, just a little advertisement, it's a new one where we can do pump-probe experiments, which means you can come in with an optical laser, you excite your system into an excited state, which lives for, let's say, I don't know, 500 picoseconds, and then you measure that excited state. Like you bring it up, and then you come with the X-rays. So then you measure it in an excited state before it decays. So that's possible too. All right, so that's kind of like the outline of the presentation. I want to talk about X-ray emission spectroscopy, which is where you have a fixed monochromator, so fixed incident energy, and you scan the emission energy. Then we have high resolution absorption. So it's, again, absorption experiment, but with a twist. And there we scan as a monochromator because it's an absorption experiment. And we keep the emission spectrometer fixed. And you can combine both of them. That's similar to an example that Musa had given earlier. There's resonant elastic X-ray scattering, where you scan both the monochromator and the emission spectrometer. And there's Raman spectroscopy. This is in pink because I won't talk about it. Just want to say what it is. It's a scanning monochromator and a fixed emission. There you measure the energy loss of a system, which means now you can measure. You ask about carbon. You can measure carbon absorption using high energies. So if you have a system that cannot really live in vacuum, you can still measure the carbon KH or the oxygen KH using Raman spectroscopy, which is an energy loss system. Like we had one example where we measured what type of carbon in a flame. So you shoot into a flame at a different position of the flame, and then you see what kind of carbon do you have there. Is it carbon oxide, carbon dioxide, whatnot. And you can imagine that's not really so well in a vacuum, but in with hard X-rays, you can measure this. All right, so first X-ray emission spectroscopy. Let's first about nomenclature. So when I excite from one S into like somewhere, it's always K. From the second shell, it's always L. From the third, it's always M. Now, when we look at the decay, then they have Greek numbers, Greek letters. So the decay into the K shell from the second shell is called K alpha. So K indicating you have the 1s involved, alpha indicating you have the second shell involved. And then you count through them, 1 and 2, coming from the 2p's. Or when you have from the M shell, which is then the 3p's, for example, it's called K beta. So K indicating is 1s, beta indicating then is the third shell. So that's when you read a paper and someone writes about K beta, you know exactly it's a decay from a 3p into a 1s. Okay, so then let's look at spectra. One is intensity. So there are probabilities for the decay. And so the decay from the 2p to the 1s is largest, meaning it gives us the largest intensity. If a decay from the 3p into the 1s, you're around 8 times less intense. And then from the valence, you're another like 100 times less intense, meaning in total, when you go from the K alpha to the K beta, valence to core, you're like 1,000 times less in intensity. And when you compare them, this here has its own scale. And then this here, the K beta, it's pretty much relative, like it's around 8 times less. When you go down here, there, that little thingy, that is the valence to core emission. Here it's blown up a little, so this one is nice and large. And here you see just a small hump. But when you zoom in, you do see that there's quite some structure. And you can, even though it's 1,000 times less, it's a very weak signal, you can actually measure it and you can get in quite good detail. And it's a powerful method. I'll explain you why. So then let's go through the various spectroscopies, emission spectroscopies. Let's start with K alpha, then K beta, and then valence to core. So the K alpha is the same as before. You're left with the 2p hole at the end. So you have spin orbit coupling, J equals 1/2, J equals 3/2, meaning again you have a splitting of the two for the 2p 3/2 and the 2p 1/2. Now they're called K alpha 1 and K alpha 2. And since that splitting is large, you're in JJ coupling, which means you can only talk about J equals 3/2 and 1/2. You lose kind of information about your spin. And so you can calculate, you get a number of features. The shape is a lot given by the interaction of the 2p with the 3D. And the position is given by the oxidation. So here's an example for 3 different manganese complexes. And when you just look at the absolute energy, you see a shift in energy, which you can correlate to oxidation. K alpha is actually quite hard to interpret qualitatively. Mostly it's the width of that peak that's most informative. And so actually K alpha is used relatively little for spectroscopy. However, in some experiments, since it's 10 times larger or 8 times larger than KB, all you want is this intensity. And then you use it even though it has less information, but it still has some. And if intensity is what you need, then you do this. Most of the time, what is used is the K beta emission, which is a very popular method. So it's a decay from the 3p into the 1s. The interaction of the 3p orbitals with the 2p, with the 3d is a little less. The spin orbit coupling is a lot less, which means for the K beta, you can now stay in LS coupling scheme, which means spin and orbit are still good quantum numbers. So you can talk about spin without like being weird. As an example I use here is manganese chloride. Manganese chloride is a D5 complex, it's a high spin, so all 5 electrons are parallel. So now when the 1s, goes into the vacuum, it gets filled by its 3p, meaning you're left with a hole in the 3p. And so I only draw one of these orbitals for simplicity. That, since you can talk about spin, it's either a spin up or a spin down in this 3p, right? And so they see each other. And now we have Hund's rule, similar to Hund's rule. They all want to be parallel. That's best in energy. And when you flip this guy here, you get a different energy because they all interact with each other. And it's at a higher energy, meaning a lower emission energy. And so that's where these 2 peaks come from. This strong feature here is where they're all parallel. And this one here, the K beta primed, this should be a prime, is where the 3p is anti-parallel to the 3ds. And then you see more structure here where you have DD transitions. Now, an interesting question is, of course, let's assume you have a D6 low spin complex. And the T2G orbitals, they're all fully occupied. You have a spin equals 0. The EGs are also as equals 0 because they're completely empty. So since you have in the 3Ds no spin, it doesn't matter if the 3p is spin up or spin down. So what we would expect is that this peak here goes away. And that is actually what is observed. So here I have a range of complexes from a singlet all the way to a quintet. So for the high spin, you see the kβ prime being high in intensity, and for low spin, it's low in intensity. And you also see that the main feature here, it goes down with increasing spin and it moves out to higher energies with increasing spin. So you have very clear fingerprints for the spin in your system. And the reason that you have here some intensity also for the low spin is because of the DD transitions that I mentioned here. These parts, they play a role here. That's why it's not just like this single peak, but you have like a shoulder here. But this guy here is basically gone. And so you can use that for a number of experiments to figure out what is the spin in your system, the effective spin. And here now I'm want to go through a couple of slides that explain what you can do qualitatively. And it's all comparing to references. So one is integrated absolute difference. You take a reference, let's say a low spin, and you measure a complex that you have, and then you get a spectrum out, you subtract them, you take the absolute, and you sum it all up, and it gives you a number. That number, actually, as it's shown here, is pretty much linear with a spin. So just by comparing your spectra, you take, let's say, high spin and low spin and an unknown complex, and you know what the integral difference is, integrate absolute difference, and then you say that's a spin. And here the example is lanthanum cobalt oxide, which has a spin transition with temperature. And so at low temperature, it's low spin. At high temperature, it's high spin. And so they measured at a bunch of temperatures here, and you see this feature going up, this one here going down with temperature, hence with increasing spin. This is a difference spectrum relative to the low spin. You integrate it, or you take the absolute, you integrate it, and you get a number, and they plot it here. And so here you can see then how, with temperature, your spin changes. And that's a very nice quantitative estimate even of your spin in your system. Another one is, since we have seen that the peak here, the first peak, which is called kβ13, that it shifts in energy with different spins. So what you can do is just take the first moment. First moment is the same as the center of gravity. You take the first moment of the kβ13 and you plot it. And again, you get a linear relationship. And you can use that even for systems that are quite low in intensity and there are mixed valence and mixed spin. And so this here is for photosystem 2. Here, that's a Koch cycle. And I'm not sure how familiar you are with it, but that's like you start with a system. I forgot. I think it has the dark state is manganese 3 and 4. It's a mixture of them. I think it's 3 manganese 3, 1 manganese 4, and then you excite it with light. You switch one from 3 to 4. You excite it again with light, another one 3 to 4, and you do that 4 times, and then at the end it comes back. It does a water splitting and comes back to where it was. And so you only change 1 out of 4 manganese. So you only have a change of a quarter, and you change it by 1 spin. So it's not a big change, but it's big enough that you can measure it. And so here are the spectra, 0 flash to 1 flash, 1 flash to 2 flash. The difference are very small, right? So if you look at it like from a distance, you say that's all the same. But when you look at the first moment, then actually it does turn out that you have small changes, systematic changes. And so with that, you can actually measure relative changes in the spin. And then you can see that actually one of them has changed. And by the way, spin is connected to oxidation state. So here in In the photon system, the manganese does not change its spin, but it changes the it does change the spin, but it doesn't go from high spin to low spin. It then changes the oxidation, hence it changes its spin. And it has also, these are again, it's a pump probe experiment where you excite your system, and then with time you take many spectra and you plot them. These are the different spectra, and you can actually identify intermediates in your spectra just by using the Kabeda method. All right. As another thing to say, what you actually measure is the effective spin. So when you have covalent mixing, for example, you change your spin, right? And so what you measure basically is an effective spin of the system. And crystal fields for the low spin cases can actually also affect it. Valence to core, the last of the emission spectra. You follow the decays from valence to the 1s. It's a very weak system, a very weak signal, but it can be measured. And that's pretty powerful. When you think about it, what you end up, you fill your 1s hole, and you're up with a hole in the valence, which is exactly the same final states when you do a valence photo emission. So you come into with a photon, and you kick out a valence electron. Final states are identical. And so here is a spectrum of a photo emission signal. That's, I think, iron 2 or 3 probably. And underneath is a valence to core emission. And turns out, when you compare these, this feature here, what's called KB satellite or KB double prime, originates from the oxygen 2s. Like for photo emission, that's all very much known what the features mean, and you can just correlate them here. And so then this here, so that's coming from the ligand, from the oxygen ligand, almost exclusively, even though you're exciting at the iron. And then this one here contains a ligand. So the wave function has a lot of ligand character that you reach. While the iron, the real iron, that's an iron like D5 system. D4 means, right, you have kicked one out. We don't really see that here. So from there, you learn that it's, by comparison to photo emission, that it's very sensitive to the ligands of that specific iron. And actually, they did another test where they changed here the ligand, the type of the ligand, fluoride, oxygen, nitrogen, which have different binding energies. And so indeed, so the photo emission, they change position because it's binding energy. And you indeed see that they change quite a bit here. So this satellite reflects what kind of ligands you have, what kind of ligand characters. And the intensity here, that you're actually measuring the ligands, they have shown that here by making the manganese oxygen distance larger, and the larger it is, the less you overlap and the lower the intensity. So you measure the ligands, which is actually very nice. Here's another experiment with manganese 3 terpy, with different outer ligands, and you see that the spectra look very different because you have changed the ligands of the manganese in this case. And you can actually nicely simulate them using ground state DFT, which works very well. So you have also a quantitative ability to describe the spectrum. And it's actually so sensitive that you can compare this compound 1, compound 2 and compound 1. Oops. One is an OH and one is both compound 2. One is an H and one is an O ligand. So the difference is only one hydrogen. But you see a small change here in the satellite. I mean, okay, these are simulations, so there you always see things nicely. But I have seen an experiment where it actually, you could see a change in intensity there. So it's a very powerful method that gives a lot of information about the ligands. So you have K-beta, which gives you like the spin, effective spin. You have valence to core, which gives the ligand information, just with low intensity. Then there's to absorption again, absorption with a twist. I didn't describe that previously, like how you actually record an absorption spectrum, but you scan your monochromator And then you excite in 1s into 3D. And of course, also the 2p will decay into 1s. And you measure that emission from these photons. And so this here is a simulation of iron and water. And you have a lot of feature of intensity here. That's an elastic peak. Not every photon will lead to an absorption process. Some of them just hit the sample and then somehow make it into a detector. So that's the incoming energy. Then here it's something that's called Compton scattering. It's an inelastic process. And then here is where the K-alpha emission is. This is measured with a so-called germanium detector, which has a very bad resolution, like 200 eV, which means you cannot discriminate this K-alpha spectrum that you measured. But you don't need to, because you want all the photons, and so you take all the K-alpha photons. So you have a higher signal, and then you measure an absorption edge that looks like this one here. That's RTPV bismuthazole. That's in D5 low spin. Here you have an idea. That's where the T2G orbitals are, and this here is where the EG orbitals are. And then you see the shape resonance. Now, if you have an emission spectrometer in the middle, then you can select specifically which emission energy you want to measure. So instead of like summing over the whole K-alpha, you only select like little slice. And so when you do that, what you actually do is you increase your resolution dramatically. And so the same spectrum for the same complex, the pre-edge here, now looks quite different. It has the same content, basically, but the T2G now really stands out. And here where the EGs are, that's actually a very, very quick spectrum that I took without really a lot of care. And still it gives you a very good spectrum. And also the shape resonance comes out better. And so the reason, the reason why it's so much better is, first we have basically no background. Like any of these here that would make it into your detector in the other way, we select them out. So there's practically no background. And you get very sharp spectra because you have 2p hole involved now that you measure. And here's a little example given for, that's an electrochemistry example. Is platinum. In black is the total fluorescence, so the normal absorption, and then what's called HERFT, what I just described here is high energy resolution fluorescence detection. It's given in red, and it's very sharp. And so here are a couple of results. You change the voltage, and so you oxidize it or make it more metallic. And you can see very small changes that now stand out. And so that is a method where I would use high resolution spectroscopy, because you can see fine differences. All right, let's go to the last part, which has, I don't know, let's say 8 or 9. Yeah, we can wrap in 10 minutes. So it's a complicated slide, but I walk you through. So we think about a D5 low spin complex. So that's a configuration. You have a hole here, and so we have two options. We can excite from 1s or from the 2p into it. When we excite from the 2p into the 3D, we get an LH, which looks like this here. Very sharp, very nice. When we excite from 1s into it, we get the KH, the pre-edge, because it's excited in the 3D. It looks like this, which is way broader because of the lifetime broadening. And so when you compare these two, it's kind of clear you want to go with these here. However, they require soft X-rays, require vacuum that might not go so well with your system. So what we want is we want the benefits from the soft X-rays by using hard X-rays. And so one can actually do that by combining absorption and emission. So when excite from 1s to 3p, sorry, to 3D, you have an electron here and a hole here. And as I said before, this hole gets filled with a 2p electron. So we end up here. And so the final states are identical than what you would reach with an LH. But it's all hard X-rays. You only have to scan now the absorption energy and the emission energy. And so that's how the spectra then look like. They're then two-dimensional images. Like here's the absorption energy, here's the emission energy. Actually, that's the difference between the absorption and the emission energy. That's what's plotted here. And you see very nice features when you integrate in this direction here, you get the KH again. And you integrate in this direction here, without the rising edge, you get something that's LH-like. When I say LH-like, you have to be like a little careful with how you interpret data. And that also is the same as like this HERF, what I described before. Because the HERF is where you have a fixed emission energy, which means it's a diagonal cut through the Rix plane. And so this is a little bit like a slice of warning. When you take a high resolution Rix plane, you see that's an RM2 high spin, where we know before we had 3 peaks, right? You remember from the Tanabe-Gano diagram. You see them. Here's the first one in absorbed energy. Here's the second, and here's the third. But they all also have partial intensity along the emission energy, which are then so-called off diagonals, which means when you do a diagonal cut, you don't hit all the features right at its center. So the intensity distribution is not exactly what you would expect, because you're missing this intensity, for example, when you drive through. So there you have to be a little careful of how to interpret the relative intensities. But big advantages, you will get these. All right. Again, that's basically a comparison, like how well the Rix works compared to like a normal KH. What's also very prominent to see, since these are two-dimensional planes, you can very clearly see individual features. And so here, this is again D5 low spin. That's the excitation in the EG, that's excitation in T2G. And it's very clearly separated. And that's because it's a two-dimensional plane. And so when you can measure anything two-dimensional, it's always an advantage. It takes longer though. All right. So I said before that we want to have an LH-like spectrum using hard X-rays. And we want it because of the resolution. And so we test that. So the nice thing is that with a KH, we can select the transition. We know we have the T2G and the EGs, and that's ferricyanide, which has a pretty pretty strong crystal field, so they're nicely separated. So we can excite in this feature, which we know is from T2G, and then measure the emission energy. So do a vertical cut, which is LH-like, and then compare it with an LH, and actually it fits very nice. So the broadening that you get, you're not lifetime resolution limited anymore. You're only limited to how well you can actually bring a beamline or align the beamline. And that has been used in the past. That cytochrome C, the same example what I gave before, where we try to figure out, can we use Rix actually and get information about the electronic structure? And you can. I don't want to go into any details because it's very late, way over time. But you get more information now by doing vertical cuts, and you can interpret these also in terms of differential open covalency, since you can also, with the same methods Mario will describe them. And with that, I'm done. That's a summary. It's powerful. We can do it. You can reach basically every element periodic table. There's huge range of crystal, like big crystal banks. You can measure the emission spectrometer, spectra, and you can measure it at almost each environment that you're interested in. There again, more articles for you when it's cold and dark outside. And with that, I'm done. Thank you. And sorry for being so late.
Maybe we have time for one question.
Hi, Thomas. Thank you for your talk. I learned a lot. I have a little question, maybe stupid, sorry. But how can you know that in your spectrum you have a very weak signal? Is this signal is from the ligand and is not really a noise in the sound? How can you discard noise and a weak signal? Thank you.
You can by measuring longer. So the noise, if it's Poisson distribution, then the noise is 1 over n. Like you have n photons, the noise is 1 over n. Which means when you have a signal that's very noisy and you don't know, like, there's a little feature, and is that, is it accidental, such as the noise, or is that my signal? Then you measure twice as long, and your noise will go down by a square root of 2. If that's not enough, you measure 4 times as much, and then compared to the initial one, your noise is down by a factor of 2. And so when something is too noisy and you're not sure if that's really a feature or if that is just like noise or accidental, you need to measure longer, keeping in mind that when you measure twice as long, the noise will go down square root of 2.
Well, let's thank. Let's thanks again, Thomas. And we have some lunch now.
Yes. So those of you presenting posters, the poster stands are ready. And Victor, right here, has the pins to put them in. There's no program, there's very few posters, so just pick your favorite spot and we'll go through them during lunch or coffee. And we will adjourn 15 minutes later, right? So that we don't rush for lunch. So 2:30 we continue here.
Ahí ya debes de escucharte.
Hola, hola.
¿Te lo puedes guardar? Anda.
¿Ah, sí?
Sí, perfecto. Así, fabuloso. Y sí pasa, ¿verdad? Ya. Es.
Pero si quieren que apague. Sí. O sea, no sé si ayuda o voy a empezar a moverme aquí enfrente. No, no. We are perfectly on time. I can't whisper. My microphone is already on. Hay que me presta mucho más. No, no, no. Actually, Victor's.
So we will continue our program. Welcome back. And so our next speaker is Dr. Niels Schut. He's a physicist by training and did his PhD in the Free University of Berlin, where he gained all this expertise in X-ray absorption spectroscopy, studying metal centers, heme centers, cytochrome and so on. He'll tell you. And since almost 4 years ago, he joined Simba staff as a postdoctoral fellow, and we're very happy to have him with a fellowship from the DFG, which is a very big distinction. And so he will tell us about extended X-ray absorption, fine structure analysis. And
yeah, thank you very much. Normally you say like, thank you for having me, but I organized this, so thanks to myself for having myself. That's a new one for me. So yeah, I will talk about the structural part of X-ray absorption spectroscopy, which in a lot of senses has become, to the staff scientists at Synchrotrons I've talked to, is like the bread and butter of X-ray absorption spectroscopy. It's a little boring for the staff scientists, but there's still a lot of exciting potential for especially bio-XAFs, as Kelly and I and Liliana are primarily interested in, right? It's not the most fanciest of techniques in a lot of senses, but also a readily available technique around the world. And in a lot of senses, I think we are in a kind of golden age of synchrotron spectroscopy, where we might come on the verge of having maybe too many synchrotrons, which makes it way easier to get beam time and for new users to get experience. So I think that's a good opportunity for anyone who is interested in doing that to actually start with that. And as I'm the last talk for today, I thought that I summarize a little bit what we have seen today and then go into the X-ray analysis itself. So where would we like to do our work? At synchrotron facilities around the world. And what are synchrotrons? Well, these are these enormous facilities, football stadium sized facilities that feature the linear accelerator, which produces the electron in bunches close to light speed, close enough to call them essentially at light speed. When you do the calculations, you come up at 99.9997% of light speed. And I'm like, yeah, okay, that's light speed. They get accelerated, for example, here at the ESRF, where I took this image from, to 6 giga electron volt. And whatever calculator you find on the internet above 4 giga electron volts tells you just it's one C of speed. In 50 milliseconds, in 1/50 millisecond frequency of separation between these bunches. Then you have the storage ring where all the X-rays are created, and which feature all these X-ray creation devices, bending magnets and undulators, and you have all these beamlines, which if you are at the synchrotron are these little nuggets of science where if you have the minute to walk around and do a little walk and see what these people are working on, and essentially you understand no one who you ask them. It's an interesting experience to go around and ask them, what are you working on? And you don't understand a word they are telling you, because the diversity of topics that are being studied there are so enormous. And so as a user, the first thing I usually think about whenever I go to a beamline is what is the insertion device that is being used at the beamline I'm currently working on. So you have the storage ring, and then you have these different insertion devices, which can either be bending magnets, which is the most direct way of creating white line X-rays, or you can have undulators, which are these arrays of magnets, essentially individual bending magnets, but way stronger, that force the electrons on these wiggly path, and at each point they create X-rays and create X-rays with a higher brilliance, with a higher photon flux. And for me as a user, this means I need to think about how how fast I can collect the spectrum, and how photoresistant my samples need to be, especially for XRFs, where acquisition times can be in the realms of hours for bioXAS samples, right? For enzymes, for just metals in biology in a sense. So while undulators are usually from a bullet point view a better insertion device, what essentially happens if I do bioXAS, I just put enough aluminum foil in front of the beam to just throw away 90% or 95% of the photon flux, because my samples won't survive the X-rays, the pure X-rays from the undulator itself anyway. So essentially I make an undulator into a bending magnet again, in a sense, because at the end it's roughly the same photon flux again. I thought I always like to see all of the spectra I collected during my PhD and postdoc at once, because it does showcases again why it's such an amazing place to do experiments, because you can look at the as before mentioned absorption and emission spectroscopy parts. Just see these small spaces or in energy where I can do experiments on just one particular thing I'm interested in, and really put myself into the shoes of the element I am currently investigating. So if I want to, there was a question previously, right? If I want to look at one element and then at the other, I can do it on the same sample and just focus on one particular sample in a sense. I can do it in a variety of conditions, in gas, liquids, solids, low temperature, high temperature, low pressure, high pressure, whatever my heart desires. X-ray absorption spectroscopy, especially KH X-ray absorption spectroscopy for transition metals, is there to facilitate your needs in a way, if you find the correct beamline. Sorry, that was wrong. Here. So coming now here to the so-called, I would call it the spectroscopic landscape. You usually are interested in if you're doing transition metal X-ray absorption and emission spectroscopy. Thomas talked previously here on the XAS part on the pre-edge and the X-ray absorption near-edge structure. On the X-ray emission spectroscopy part, the K alpha emission, K beta emission, and K beta prime, K beta 5 emission. But what I'll be focusing on now is, what if you ramp up the energy even further and further and further and further, and just doesn't stop? Like Thomas is interested in maybe 100 electron volts of energies, and I'm interested in a few hundred electron volts of energies more. And what we reach then is the so-called extended X-ray absorption fine structure region, so XFs. Where does it originate from? Well, if you here again, we have a lot of talk about iron, because iron is pretty interesting in many senses in biology, but also in chemistry, because it with its 3d6 configuration has access to a lot of spin states and oxidation states. So usually everyone has done iron at some point. And when you look at the spectra itself, the KH absorption spectra, the X-ray absorption near-edge structure shown here originates from the absorption of a photon that creates an electron core hole, and the transition leads into an 4p occupation of this electron in rough senses, of course. Thomas went into way more detail into that. And what I'm interested in now in showing you is, what if the electron itself leaves the element altogether and just becomes a free electron, and this is what we would call a continuum state. How would we measure that in general terms again? We start from the bending magnet, in this case with a white X-ray beam. Christoph showed very nice images of how this would look like, Star Wars like. the X-ray beam hits the double crystal monochromator, which selects the energy, absorption energy we are in this case we are interested in, and define the element we want to investigate. Then we measure the photon flux before our sample. Then the X-ray beam hits the sample itself. Something happens, gets absorbed or it doesn't. And we measure the photon flux after the sample. And what we see here is that before the sample, we have just dependency of intensity by selection of the monochromator and the white line intensity. And afterwards, we see that there's this steep absorption edge. And what's happening, of course, is that the element in question, if our sample has the element in question, that's not always the case, has absorbed via and it's showcasing here the absorption coefficient, which if we put that together in an absorption calculation with I0 being the beam photon flux before the sample, I1 the beam photon flux after the sample, and we have an exponential absorption due to the thickness of the sample and the absorption coefficient that depends on the energy where we are exposing it to. And then we get our nice, clean absorption edge and features we can analyze in future steps. And then we get XFs, and then we just analyze it, and the magic happens. So in this case, this is a spectra we will look at in the workshop, in the hands-on session afterwards. Just zinc in EDTA is a cool, nice reference. We get these wiggly lines here. We get the Fourier transforms of these wiggly lines here, which are due to the absorber element emitting a photoelectron, which interacts with the surrounding nearest neighbors and can either have constructive interference or destructive interference, and which can lead to these modulations in absorption intensity. And what can be done afterwards, if you have the right tools and knowledge of theory, is you can modulate, you can simulate the appropriate eccentric absorption fine structure by just inserting more and more elements. So here we see nearest neighbor zinc oxygen distance, then the other zinc oxygen distance in the planar and axial dimension, and then the nitrogen distances. And this can be increased further and further, now going into the second sphere of the carbons. And at some point, our simulation returns to us that there's essentially no change anymore by adding more and more distances. And then we're done. We have now successfully analyzed how zinc binds to EDTA and are happy with our analysis. Well, this is, of course, this is essentially the extent of what anyone is finding in a publication, so to speak, right? And most, if not all, readers are lack the insight of judging what's behind all of that. So and this is something I would like, this is the point of the talk today, like how do we get to understand this magical appearance of other wiggly lines that add up to yield the information they are now presenting to us in the paper. And as I am a physicist by trade, as was mentioned by Liliana, I like formulas, and that's why, and I think the X-Hubs equations that were also mentioned by Christoph are actually quite nice. And so bear with me, and we will derive the X-Hubs equation from scratch. Yay, formulas. So what do we, yes, I think it's very beautiful. I hope to convince all of you. So what we have here? We have the Zanes region, we have the X-Hubs region. And essentially we can separate them into three parts. One is the actual edge jump. In this case, delta mu 0. The other one is how the edge would look like if it was just be an edge, so to speak. So that if you would have absolutely no modulation of that, we would just have the plain edge, so to speak. So delta mu0 and mu0 of E. And what we have left now is chi, which in a general broad sense is what X-hubs is about. So expressed in formulas is that sorry, I missed mu0. That the absorption coefficient itself is the plane mu0 edge or absorption modulated by this factor chi here, right? So chi itself is then just rewritten the same formula, mu over mu0 minus 1. But what is mu0? What is the absorption coefficient itself again? Thomas already mentioned it. What it comes down to in the end is always Fermi's golden rule. So we have some sort of initial state, we have some sort of final state, and we have a Hamiltonian that connects all of that. And this is written down here in bracket formulation. I hope everyone is familiar with that. If not, I'm happy to explain it a little more detail in the end. But what are these initial and final states? I would explain it like that. So at the start, the initial state is we have a peaceful atom that was prepared by us, and then there's this energized X-ray that wants to disturb the peace. And the final state is just that. We have the extremely excited state. We have the core hole, like the strongest bound electron of the atom itself is just ripped out of it. And we have this core electron now with potentially tremendous energy bouncing around the molecule we are interested in, or the protein we are interested in. And the Hamiltonian that connects all of that is essentially a dipole transition. You can express it in more detail. But for simplicity and just a little bit of hand waving, I would just say it's 1. Any overlap between the initial state and the final state is completely fine. It's just 1. And it actually works pretty close to that if you actually do the math. Thomas had a lot of nice review articles about that. They can go into more detail, or even at the source, which basically all of that is based on. You can find more details on that. So, but what is the final state if we separate it now after thinking about it? So the core hole and the photoelectron. These are almost independent, right? We have for example, iron or zinc or manganese atom, which is now very excited. And on the other hand, we have a free electron, which does whatever it wants to. So in the first approximation, we can just separate these two states, which makes the final state a superposition of two states: the core hole excited atom and the free electron. And with some hand waving, just trust me, with some hand waving, we can say, okay, it's just a separation of these two states. And if we now look into this formula, these formulas again, we can already tell that it's quite similar in a way, and I can just approximate that the modulation of the absorption coefficient at higher energies is just due to the interaction of the photoelectron with the surrounding matter. And if you think about the example Christoph put at the start of one of the first spectra with I don't know what element it was, but in the gas phase, which is where the edge itself and the X-ray absorption fine structure was almost unnoticeable, and then it solidified in lower temperatures, and there you suddenly saw the rise of X-ups or the fine structure intensity. And it's essentially that once you get sufficient that this part is always present, but this part might not be present in the sample you're looking at. Right? So second part. We now only want to focus on the initial state and the photoelectron. What is the photoelectron itself? In a lot of whenever you read up on EXAFs, the first example you might encounter is like a comparison to maybe pool billiard or something where, well, the electron gets ejected and then it just bounces around the surrounding atoms or whatever. But this is only partially true in a simplified manner, because essentially when the absorption occurs, in this image, the electron has not yet interacted with the surrounding atoms. So why is the absorption coefficient itself modulated by it at a later time interacting with the surrounding atoms? But rather here you see this is a quantum mechanical problem. So it's not about an electron being ejected, it's about the probability of an electron being ejected. So we are talking about electron as a wave function and not electron as an actual already left entity that is then hitting another atom, another ligand. And this is what so if we now write that down as an actual wave function, right? We want to think about the initial state and the free electron. Well, the initial state essentially, as I told you, the only difference is the electron bound itself, right? And if now we have a 1s electron question. What is an 1s electron in terms of radial distribution? It's essentially just a delta function. It's almost exclusively very close to the core of the atom itself and nowhere else. So the 1s electron function is essentially a delta function. And the free electron is the first problem you solve whenever you have quantum mechanics in any course, right? It's just n exponential. Well, it's actually n spherical function that goes out from the point. And so it's just depending on energy and the radial position. And now if you integrate over all positions, the delta function is only present at r equals 0, because that's what we defined as the center of the problem, and anything else is irrelevant. So we already know now that the chi itself, the EXAFs we are looking for, is just the overlap integral, or it's just the intensity of the electron wave function at the core itself. So we have reduced the initial problem quite dramatically into into thinking about a I don't know what's it, the quantum mechanics 1 first week problem. So this is pretty amazing, right? So what's the actual solution of the free electron wave function? It's usually not expressed in terms of energy. It's usually expressed in terms of wave vector k, because it's how it's usually modulated in the solving of it, because of the momentum wave, the momentum operator, which is then transforms energy into k. And just as a reminder, here's the expression for that. And I think in the end, this one is 0.27 in electron volts. So if you just have that, you can get it easier. But what is actually the magnitude of the free electron wave function at r equals 0? We created the photoelectron at the center of the absorber of our problem, the first atom, the absorber atom. And then it's the photoelectron wave function spread out and interacted with the surrounding, with one surrounding atom in this case. And what is creating then is it gets reflected to the absorber itself. And two, it's one, it's modulating its intensity, and the other, it's introducing a phase transition. It's changing its phase with respect to its first self. Just think about it as the electron itself is, depending on what element it's interacting with, it takes more or less time to leave the element again in terms of charge, for example. And then we have the initial wave function again, but just returning to the absorbing atom, plus some complex conjugates, which we just ignore because it makes the math work out. But what I want to take away here is photoelectron gets emitted from the absorber. It interacts with this one surrounding atom, and it comes back again to the absorber. Because remember, the only thing we're interested in is what the magnitude of the photoelectron wave function is at the absorber. So what are these factors here? F of k and delta k. So one is here shown here, the X-of scattering amplitude, which depends on the element the photoelectron is interacting with, the photoelectron wave function is interacting with. And it's plotted here against the wave vector k, which essentially tells you how much energy the photoelectron is carrying. And as you can see, here we have oxygen. The magnitude of the X-of scattering amplitude is has its maximum at a lower k value than, for example, for iron. And this is one of the principal ways how X-ofs can tell you something about the elements the electron is interacting with. Because if it's interacting with a close iron partner, it will have a higher amplitude of interaction at higher energies than, for example, if the surrounding atom would be oxygen or nitrogen. And this is what, when people talk about X-ofs yielding elemental information about surrounding atoms, this is the principal reason for that. So when you now introduce the complex conjugate into all of that, you essentially end up with the sine function, the complex exponential function then transform into this sine function. So this is now the X-ofs formulation for a single atom. We have one absorbing atom, we have created one photoelectron, and it has interacted with one atom. A single atom J at distance R. And the other factor I've introduced here, due to space reasons on the other slide, it's the X-of scattering phase shift, which is important, but a lot smaller in its elemental dependency. But these are the two factors, the phase shift and the scattering amplitude dependency, that yields information about the elements that are surrounding our absorbing atom. So again, we have now solved it for a single atom J at one distance R, but we usually don't have just a single atom surrounding our absorber, right? So thinking about what could be the solution if we have more than one atom, but all at the same distance. Well, it would just include the number of surrounding atoms. So you now have a perfect hexagonal octahedral perfect configuration, then n would be 6. But there would still be an error, because if you now we are approaching reality closer in smaller and smaller steps, the 6 atoms usually are on average at the same distance, but they are not on the same distance all the time, right? They vibrate, they move around, and so they have some displacement to themselves all the time. And this is what is introduced in this factor here, which is the Debye-Waller factor, which just represent, if you have 6 atoms going back to perfect octahedral, 6 atoms surrounding our iron atom, for example, they will have some displacement due to temperature all the time. This is one of the reasons why experiments are usually conducted at cryogenic temperatures or even lower. So you have at least because we are slowly going to introduce more and more factors, this lets you control one of them at least. So, okay, n atoms at of equal element and equal distance, also very unlikely to be the reality for all our samples. So in reality, we will usually talk about a number of atoms of different elements at different distance, right? Can be four ligands of, for example, nitrogen and oxygen in a planar configuration or tetrahedral configuration or whatever configuration you're interested in. Anything between 2 to 6 or even more, even less. Atoms can now be covered by this formula. And remember, the only thing that is actually that we actually need as a rather complex description are these sign functions. So we are just, as I remembered from the quick go through of what analysis usually looks like, it's just think of it as sign functions. And why we introduced the K vector is also immediately clear now, at least visually here, because it's just easier to imagine periodic sign functions instead of square root of e minus e0 sign functions. However, what we have for now omitted completely is the possibility of the electron to interact with anything outside elastically, right? And it's actually one of the important parts. If our electron loses energy in any process, it's essentially lost for this analysis. So what we need to think in the last step is, what is the photon electron mean free path? So how far can an electron in general travel without losing energy and still return to absorbing atoms? Or how blind are we at different energies? Because it's not symmetrical, right? So if I create an electron with different wave vectors, it can reach further and further and further for higher energies, but it can only see nearest neighbors for lower energies, right? And now you can essentially say, so depending on how high, how large I choose the K vector or the energy I want to reach in my measurements, this is how far I can see with my electrons created by at the absorbing atom, right? So at the start, at the minimum, I can see like 5 angstroms. So I might potentially just see first sphere and second sphere elements. Or I can go even further, but here with increasing K, you will see that the entirety of the measurement becomes more and more longer, more and more difficult. So we can now include as well the free photoelectron mean free path shown here, and another exponential function. And just to round it up, because you need something to fit it correctly to the actual data, there's now this S0 term, which is essentially just one factor that translates all these formulas into the actual measurement. And this is element specific and usually chosen to be a number that you find in literature or something. What's the last one? Yeah. Okay. Yeah.
What's up with lead over there? Is it? Yeah, but this abrupt change in body. Okay.
So it's the interaction of the electron with heavier elements becomes more and more complicated. So the more shells you have, the more difficult the stranger the interaction becomes. Why this phase shift at higher K values? I actually don't know. I think Mustre would be a good one to ask, or Christoph. Well, people who wrote the FEF code and got way deeper into these technicalities than I ever did. Yeah, you need these to, as you can see, you need these to correctly model the interaction once you really want to simulate the spectra. Both.
Yeah. So I guess my question was more that that shift is real.
Yeah.
Because I mean, it looks to me like it could be
Yeah.
a baseline shift or something.
No.
But no,
No, it's
real.
essentially you have the one sine wave that goes out from the absorber. It interacts with that and then it comes back, but it comes back at a phase shift. So you have the overlap of the two. And what you need to then imagine is if the larger the phase shift, the K dependency, the energy dependency of having then a constructive interference is different for different elements. Right? Christoph?
No, I know it's for the.
The tubes.
Yeah, no, you're perfectly right. And I think, I'm almost sure, it relates to the different shells of electrons. And so you have discontinuities as you add more electrons, because when you have a wave, it bounces back, and that's a phase shift. You know, it's a potential. So you have to derive the potential of the wave when it arrives at the vicinity of the atomic potentials, and then bounce back. I mean, of course, it's a picture; it's not real. But and then depending on the electronic structure, you have discontinuities in there all the time. So the more electrons you get in, the heavier the atom, the more discontinuities. And that's actually why calculating the phase shift with a code like FEF is so important, because it does a calculation. It's an Hartree-Fock calculation. So it's with muffin tin potential. So it's average. It's completely spherical, but it's not bad at all. Before that, they just draw lines, and we had tables before FEF. Actually, we had tables. It was called the Mac. Do you remember? No, you don't. Okay.
Do I remember?
Well, I don't remember the names, but we had tables, and for you take your central atom, you take your backscattered, and you were looking at your tables, and you were just entering a straight line. And so, of course, it was a big mistake. I mean, a big approximation, not a mistake, compared to a calculation like FEF, because
I was just gonna say something. Is that okay? Okay. I will. Something interesting is I've worked with some lead proteins, and also I've done some silver XFs, and it's really difficult to simulate things like lead in sort of more standard programs. You do really need to use something like FEF to be able to do that. It's not impossible for anyone who has interesting proteins that you want to explore that. But for silver, for example, you really don't even start getting oscillations until way out in decay space, and you can't really model that normally. But again, it's like the simpler the better when it comes to the larger stuff. It's so interesting.
Yeah, very cool. So I think that's the reason why I wanted to go into the details of this of solving these the XF's problem itself, is I think it's quite remarkable that you have this rather complex mechanism, right? You have the high energy X-ray, you create a core hole, super hard to calculate. You get the free electron that interacts with all of that around, and you think, oh, that's definitely very hard to calculate. But no, you rather end up at this rather smooth formula that it describes all the processes involved, and that's why I think one of the strengths, and based on a lot of work of not past generations, older synchrotron users. Yeah. And just standing on the shoulder of giants, right? That path paved the way to get all this done easily now on your computer while you drink one sip of coffee. And to re-emphasize that now in a more graphical sense for anyone who is more of a visual learner, the same now, but as a graph. So we start again with the absorbing atom and the X-ray comes in. The core potential itself, for all the who are interested in the theory, as Christoph just told us, it's just a simple what's the muffin tin potential is the official official term theoreticians use for that. Very simple core, very simple potential. And if we would just have an absorbing atom without anything surrounding it, so for example a dilute gas we are interested in, the outgoing photoelectron wave function would have very little to interact with, and thus the modulation of the absorption itself would be quite small. But once we introduce surrounding atoms, scattering atoms, the backscattered photoelectron wave function itself becomes modulated depending on the energy. And then when we look back, remember we are only interested in the photoelectron wave function at the core itself of the absorbing atom. Then this is the only reason why we, well, not the only reason, this is one of the reasons why we get modulations of the probability to find this at the core, and thus we have modulation of the absorbing coefficient at higher energies. And this is what we are. This is what these equations may allow us to understand and simulate, which is again here as a summary with all this beauty. I hope you can now appreciate the beauty behind all of that. So we have only a few things we are actually going to modulate in the hands-on session tomorrow. But what we are interested in are the absorber backscatter distances, usually. The coordination number is usually an open question, or at least something we would like to verify in the best case. In worst case, we have no idea, like Victor was saying. What we are not interested in, but we need in order to understand the data we are looking at, is the mean square deviation, so the Bivala factor, the x-axis amplitude, which TEF magically spits out for us, and the x-axis backscattering phase shift. Again, FEF code delivers that. The photoelectron mean path is pretty well understood and habilized, so it's just taken out of that. And everything else is provided by us. We just have two things. We have the x-axis oscillation observed at a different energy, or rather wave vector. So we have the two-dimensional, well, actually a one-dimensional problem, one observable, one dependency, and we have all these factors that go into that. So as you can imagine, if you would like, you can actually model whatever you want in that. So the core, the most important ingredient to understanding and analyzing all these data is the user itself. And so we need to become informed users in order to be able to understand and interpret the experiment we are conducting. Because in the end, what we are looking at all the time are all the squiggly lines. They look almost the same all the time, except for an experienced user, which gets all excited about these amazing shifts and the shift in amplitude maximum, and then tries to tell his lab mates, and no one cares because they don't understand the thing. But okay, that's just sometimes how it happens. And here's how it would usually look like. You end up with a successful beam time. You come home exhausted, and after a few months, you finally take out the data and look at it. And you look at it immediately, but then for publication, it's months. So what you end up with here in this case, it's zinc. I know that because that's the element, the absorption energy where zinc absorbs, and I collected it as well. So you have the edge itself with its, which is modulation chi. You fit a you fit a background into that, and then you have the chi itself. Remember, it was mu over mu0 minus 1. So it's just an oscillation that goes from this oscillates around 0, right? In this case, from -1 to 1. Against the kinetic energy of the electron itself, because the fit itself also starts at a certain energy, which you infer is the energy at which the electron transfers from being an electron bound to the atom or the molecule itself and becomes a free electron, whatever free means in a way. But what we actually are interested in is the wave factor k. And already you see by this change here that k itself is modulating the frequency or the frequency of the data here. It stretched it. So I wrote down here what the individual steps would be, and with each one you have to then also imagine, remember the electron free mean path, how far you want to be able to look with the electron. Also includes larger and larger energy steps to be able to do that, right? So, and also you see that the oscillation itself gets dampened so much that they essentially become invisible for the naked eye. That's why you usually will not see chi represented like that in most publications, and I also didn't at the start, right? But they will actually be weighted by the wave vector itself. But this is only just a visualization. It's only a help for the reader, the informed or uninformed reader, to see the oscillation even at higher k values, right? Like no one can read this except the computer, of course, but we are not. So this is what you usually encounter. You now have oscillations at roughly the same distance, maximum distance, and that gets dampened over time, and you see a shape, a amplitude maximum, as well as some fine structure, which is the reason for the name, right? The fine structure analysis. So this is then the data you end up with, you want to analyze, you want to publish. Yes.
What's the reason for this band?
This one here? So why do we need it in order to have a smooth oscillation that goes around 0, oscillates around 0? The physical meaning for that, because it can bend downwards or upwards. The thing is, the white line, as Thomas mentioned earlier, can have whatever shape it wants, so to speak. It has a maximum. Usually it can be very broad, can be very narrow. But this is actually not part of the free electron. It's still bound in a sense in a 4p orbital, for example, weakly bound, of course. This is usually also the reason why you ignore the start of the oscillations. You just start to fit from here for 2.5K. It's a good value to start fitting at instead of just at 0 and say I take the white line as itself already a free electron oscillation, but it's usually not. And in order to get rid of that artifact, the polynomial itself is usually of order 3 to 5, or depending on how good your data is. And this is then the artifact of that. Otherwise, you will not get smooth oscillation around 0. That makes sense. So let's go back to the initial example. Well, almost. It's a different one, but it's the same visualization now, and I hope most of you now appreciate what is happening. So we have our x-axis oscillation here. After data processing, we can produce a Fourier transform of it. and then we start our fitting. We first introduce in this example, because we pretty much know what we are looking at, 6 nickel nitrogen distances, and the fitting itself returns, okay, this is now a distance at 2.12 angstroms. And as well, the carbon distances surrounding that at roughly 3 angstrom. And as you can see in the Fourier transform, this is a nice way of visualizing that. Each of these correspond to its own shell. This is why usually why EXAFS talks about shells and not about atoms itself. Because if you have different atoms at the same distance, it's just the same for EXAFS. It's not 6 atoms, it's rather one shell with an contribution of 6 atoms, or an N of 6. And if you were so inclined, you can then compare it to XRD and see that actually reproduces very nicely in this case, not in all cases, but if it does, it actually reproduces very nicely the results of XRD. However, EXAFS is not perfect, although I now have made you all fall in love with the theory behind it. It still has, you still need to be conscious about how much you can actually infer from the EXAFS, right? So bond angles, as you might have noticed, are just not present. You can introduce them, but the dependency is usually very negligible. So that's why no one does. The bond distances themselves are accurate, but if you have 2 different shells, so for example, if it's a distorted planar configuration with slight differences in bond lengths between the 2 opposing atoms, you might not be able to differentiate between them if you don't go to very high K values. And as you can see here, the actual differentiation between 2 shells depends on the maximum energy you go to, or the maximum K value you go to. So at a typical drawing, this cutoff distance of 12 inverse angstroms in terms of K, we would have an accuracy and shell differentiation resolution of 0.13 angstrom. Well, if you go to 16, K16, you barely scratch the 0.1, the 0.1 distance between shells. So you need to go to very, very high K values if you really are interested in differentiating between, for example, these 6 atoms if you're going symmetrical. Then another good question was, what if you have more than one metal in your sample? Well, if you're unaware of that, then you're screwed, which can happen. So EXAFS will always give you an answer. It might just not be for the question you were asking. So you need to be very aware of your samples. And as I showed you with the scattering amplitude change due to element and the phase shift due to element, what you actually lack, you get information about the surrounding ligand elements, but it might not be as accurate as you would like. So usually you differentiate easily between lighter ligands and heavier ligands. And this is already quite helpful. But if you want to ask if it's what element we are actually looking at as a ligand, nitrogen or oxygen, you might be in danger of overinterpreting the data you're actually being given. So be very careful of that. So I want to talk a little bit about the dependency we have seen so far. How does the EXAFS look like for different distances, metal ligand distances? Just to give you a sense of what you're looking at. So shown here, this is just all theory to better visualize it, because I cannot synthesize a single copper N distance. The copper nitrogen, well, the oscillation, EXAFS oscillation for copper nitrogen at 2 angstroms, at 3 angstroms, at 4 angstroms, as you can see, drops dramatically in amplitude, which is also reflected in the Fourier transform itself. So it's not just the number of ligands, it's also the distance that contributes dramatically to amplitudes due to the R1/R² dependency. Then having, but on the other hand, at the same distance, the amplitude best visualized in the Fourier transform corresponds directly to the number of ligands in the same shell, right? So this makes sense. And it's also very nice to see. Like you have two XRFs samples that just differentiate themselves in one ligand at the same distance, and it plops immediately to get the information. Okay, there's one more than there was here. And then the difference in the element that's actually backscattering itself here in an extreme example, where we have a copper oxygen distance and a copper copper distance of 2.5 angstrom. So quite ridiculous, but just as an educational example, you see the copper copper distance in the Fourier transform overshadows any other distance you would be looking at, and that's why it's this is also very much often used as a technique to understand materials that feature copper oxides or metal oxides in general in catalysis, because you get a very sensitive measure of the element of the nearest neighbor metal that contributes to, for example, chemical reactions. But how would you differentiate between in just from the Fourier transform between a ligand with just two ligands surrounding the absorbing atom or 6 ligands surrounding the absorbing atom? From the Fourier transform itself, you would not be able to, right? It would just be a difference in absorbing amplitude. On the other hand, in the XRFs itself, you see that here the scattering amplitude, as I mentioned in the theoretical part, so to speak, depends on the element. So for oxygen, it's pretty flat. While for copper, the copper as a backscattering atom, you see that the amplitude itself increases with increasing K, which is already tells you that you have a heavier atom contributing to the backscattering. It is always a very powerful tool for experienced users to just look at the XRFs and you already say, okay, so there's probably something heavier going around here, some sulfur, some cluster, some chloride, and therefore, but less ligands and so on. And all the students look at you like, what, Jedi mind trick? And then you do the simulation and then, okay, yeah, he's right, or she's right. But as this, we are talking about metals in biology, and if you understand the FEF code, you can put in whatever you like. And so as a example, I just put, just constructed how a single histidine binding a metal would look like, or a single cysteine or aspartate tyrosine. And as you can see, they can contribute quite different to your XRF itself. On the one hand, the sulfur-based amino acids shown on the upper part have a significantly higher amplitude, although it's always just one amino acid backscattering. It's just because sulfur is so much heavier, and as in the previous, oops, that's not the previous slide, this is the previous slide. And the previous slide here, heavier elements contribute stronger to the backscattering, the scattering amplitude of the XRFs. And then you have just stronger contribution, even at higher distance. On the other hand, for example, histidine is a very nice example because what you see here is this triple feature. So as long as your data is good enough in terms of signal to noise ratio, you might just look at the Fourier transform and already tell, okay, there's some periodicity of carbon contributing to the backscattering. This could mean that we are looking at the histidine binding or metal. So if you have no idea what your metal is actually binding to, which that is often the case, but XRFs is a good starting point sometimes, this can help you already identify potential amino acids you would like to, for example, point mutate and then run the sample again. And when these features disappear, then it's like, Yes, we made it. We found the important one. Yeah.
Question, the aspartate, is it monodentate or bidentate coordination? And do you see a difference?
I think it's a bidentate.
Because you would see a difference, right?
Yes. Yeah. 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 This one here. Yeah. But these are just theoretical examples, right? But especially for bioXAS, it can be a helpful measure to already have some idea how different amino acids would look like binding to metals. And what would it actually look like to have a successful, like Kelly will go way more into detail in some way, shape, or form. But what are the things I like to pair XRFs with in a project? Because usually just XRFs on its own, or XAS in general on its own, as Thomas also mentioned, is you might not come as far as with successful collaboration. And I call it the elephant in the room technique. It's XRD, of course. Whenever I am on a congress, on a conference, and I tell, yeah, I investigate metal and biologies, then immediately the first question, so you do XRD? And it's like, no, I do spectroscopy, but it's also with X-rays. And then they don't know what to ask. They don't know what to say anymore, because that's usually their go-to. But XRD can be a fantastic tool to either go into the database, of course, or have XRFs of the crystals itself, and then XRFs of, for example, protein in solution, or just whatever you want to look at proteins at different pHs where you might not be able to crystallize the protein and then get more information about the reaction dynamics. NMR is, of course, a great technique to pair your XAS with, or XRFs with, because you have this nice collaboration going on. This is actually from the talk I will present on Wednesday, where you have on the one hand a technique which only sees the ligand, and on the other hand a technique that only sees the metal. So it's actually adding each other to a very nice complete view. EPR, if you have an EPR not silent, so an EPR active element, which is not always the case, of course, can tell you a lot about what you're looking at, the amount of copper if there's a reduction in there. DFT is also, the density functional theory is a good way to, if you have nothing except for XRFs, but you know where you should find the element, well, then you can do a DFT calculation and compare the distances you are interested in from DFT and from XRFs, and then hopefully convince reviewers that you are actually making sense. One thing we have done now with the collaboration, which was very nice and insightful, is actually having it set for DFT, so time-independent calculation, have a trajectory, a dynamic of QMMM. So having the DFT part, but surrounding it with a solvent, but not a solvent, but water. There's no other solvent in QMMM, at least at the first approximation. And for example, here we have this is a preprint. We have chloroquine, zinc, and we tried different solvent ions coordinating to zinc. And we tried 4 coordinated and 5 coordinated, and then iterating through water molecules and chloride molecules with 1, 2, 3 chlorides and 1, 2, 3 water molecules. And in the end, what came out quite nicely from this trajectory, which we could then with a FEF code translate into an average XRFs. Then we could match the best match between the XRFs data and the XRFs trajectory simulation was that there were 2 chlorides coordinating and 1 water molecule. So this is also a very nice ab initio way to compare that. Actually, in this preprint, the crystal structure was the one predicting a 3-chloride configuration, while in solution it was just 2 chlorides and 1 water molecule. So XRD is a very nice complementary way, but you always need to be careful with what you're looking at. So as a first summary for essentially the introductory course into XHAFs, XHAFs is the modulation of the absorption coefficients at energies above the absorption edge. Usually it starts 10 to 15 electron volts above the absorption, the principal absorption. It represents it represents the transition process of a core electron being emitted into the continuum and the free electron wave function interacting with surrounding ligands, either in a destructive or in a constructive backscattering process, which creates these fine structures in the modulation chi, and then can be interpreted in terms of bond lengths of surrounding backscattering atoms, and yield quite accurate numbers in terms of coordination and ligand up to a certain extent. So bond lengths can be quite accurate. The coordination number itself, depending on how experienced you are in performing the simulation, is ±1, which is the same for ligand type. So carbon, nitrogen, oxygen. Usually you have to arrive with some scientific insight already, some experience, prior experience, or other data to actually say with total security that you're looking at oxygen and nitrogen. But it's a very powerful tool, for example, to investigate sulfur or chloride ligands for first row transition metal science. So here's a good point to make a small break and then go into just some random thoughts on how to perform these. And if you would like, there's a very active community in sharing slides and workshops and presentations and tutorials and whatever. And here are some of useful examples I used for this talk or just for myself to learn about this technique. I especially recommend the SSRL summer school, which is just closed like a few weeks ago. You can go there in person, or they upload everything to YouTube as well, also with examples and workshops and everything. So yeah, so if there are questions so far, you're welcome. And then I will continue, because I have like, what, 20 minutes left?
Okay.
Hi, Niels. Thank you for your good talk. Well, I have a question. When you say that that your spectrum can be a superposition of different ligand environments, in the most simple case, you can have 2 species. Speciation will be 2. And when you make your theoretical like spectrum, is possible to put 2 species in the spectrum to to get experimental.
Depending on the software you use, yes. Very much, yes. So on Wednesday, I will present an example of not a theoretical, but an experimental superposition of spectra we collected. But you can also do that theoretically, yes. You might just, with each time you do that, you come closer and closer in over-interpreting your data, because it's still just a single line, right?
Hi, my question is, with the nickel compound that you presented, the ethylenediamine, that compound can present isomers. The isomers can be seen in the SAP.
The EDTA.
No, the one with the ethylenediamine.
There are isomers. I just took that from
Optical
another slide.
isomers.
I took that from this slide. I just believed this analysis. In what way would the isomers?
Well, with that compound, we can have optical isomers, the lambda and the delta.
Okay.
And I don't know if that can be seen on the.
Like,
on
would
this
it
technique.
change the distances, or
I don't think.
then it would not be visible? Like, angles do not contribute as much to the x-ups as distances are. So if you would have an isomer that does not change distance, then you would not see the difference in x-ups. You might be able to see it in XAS, so in the edge itself. So either in high resolution edges or even in low resolution ones, like the ones we're talking about here. But if you would be able to get a hint on that? Probably not. If you would not know that prior to analysis, you would just fall into the pit of making an error in your analysis. So the more you know, the better.
Thank you.
For the people watching us by YouTube, you can write your questions in the chat. Just so that you know, I mean, everybody written in the chat.
Yeah.
Okay. We'll take,
No,
you wanna take a break or just keep
no, this was just the break already. So
Okay.
any questions? Because now I would like to talk more just about when I prepared the talk, I was like, okay, I think this is how much background I can let anyone have. And then in the hands-on section, you can actually do the X-Hubs analysis, so I don't need to show it to you anyway. So what would I like to talk about the last 15 to 20 minutes? Random thoughts, just whatever occurred to me, so to speak. So Kelly will also talk about that way better than I will, of course.
No. We can all talk about this.
Yeah. So my personal thoughts on how to get beam time, how to be successful at obtaining beam time, at finishing beam time, and be happy with the beam time, so to speak, right? So in my experience, a good rule of thumb is you will measure, you have a project and you will go 3 times to the synchrotron until you finish the project. The first time you go and you're all excited and you take your samples with you, right? You're all excited, you have this great idea, and then you take them and you put them in the beam, and then something is wrong with the sample. Just it didn't occur to you, it's the wrong solvent, it's the wrong buffer, maybe the sample holder was not adequate for the beam or the sample, the wrong thickness, whatever. Then you go back, you're all beaten down, you pull yourself up again. Okay, you do it again, you have learned your lesson, you come with the better samples, you measure them now correctly, and then you realize that the hypothesis was wrong all along, because that's usually what happens with collaboration. Someone brings you something, you measure it, and you say, whatever you thought about the sample, actually that's not true. You have now shown definitely that whatever your hypothesis itself is incorrect. And then you go back with the data, and then you discuss it as heated as you would like. And then you go a third time, finally, with the right samples, in the right conditions, in the right set of experiments that will now give you the insights and the data you need for publishing, right? Yes.
Neat story about that. I was in Daresbury at that time, and we were measuring some lanthani edges, and we wanted to do some a reference, and I don't remember if it was a European, but it doesn't matter. And so we couldn't find the edge. So we thought the beam was not inside the sample. We lost the beam, or we were not well aligned, and so we were taking photographs with paper and everything, and this drove us completely nuts for half of the night. And we couldn't understand it, repeating again and again, and we are completely lost. And at some point, we changed our reference, and it worked. And it's just because the name of the chemical on the lanthanide was not the right one. And it's not because it was not well named, it was because they made a mistake at the factory. Because it was the wrong name. Because all lanthanides look the same. That's the definition of lanthanide. So it's very difficult to separate them, and it's very difficult to notice that it's not the same chemistry unless you do spectroscopy. And then so we spent half of the night looking for something that was not in the right flask. So that's exactly the same, yeah.
Yeah, that happens. Or when you have a protein that's very well defined in concentration, and then you, for some reason, during purification, chaperone maybe overlooked or something is missing in all of that. And suddenly the beautifully purified protein of 1 millimolar in solution essentially has only 1/10 of the metal sites occupied in reality, or occupied by the wrong metal. Like if you do XRD, you usually lack elemental information in terms of transition metals, and then you actually have a protein. Yeah, you have zinc everywhere. The zinc is all everywhere in E. coli, for example, and just occupies whatever it wants. And what you actually were interested in was some iron activity from iron in the catalytic side was just not occupied. It's just not there. And then you go back and say, oh, sorry, but no. Yeah, but yeah, this is in my experience how a typical projects go. So what you usually have is like these call for proposals, which are 2 or 3 times per year, depending on where you go. You write these 2 pages. So what you end up with is you write a proposal as an unexperienced user. You write a proposal, you go with them, and then you have to tell the synchrotron, by the way, the first time didn't work because so I think that is nice at SSRL, where you can actually transmit. You send a project for several beam times, not just a single one, so you get a second chance more often than not. At VESI, where I also measure a lot, or Soleil or ESRF, it's usually just a one-hit pony, and you make it right, or you're screwed. So how would you make a successful proposal? You first have to convince a set of referees that are completely unexperienced in what you're actually using and doing. Why is your topic important? Then you have to convince them that XAS is actually the correct method to solve the problem you're wanting to address in your field. And then this is the one it's not the most important part, but it's usually the most important part. Like Christoph told at the start, if you're an unexperienced user, you just don't get the beam time. So why are you the perfect candidate to try? Someone else could. There are a lot of experienced people around the world. Maybe they should just send your project to them and they should do it. So why are you the perfect one to do that? And this is usually the tricky part for an unexperienced user, because I don't know. Like that's the definition of unexperienced, right? So the better you are at understanding what's in your sample, talk to anyone who is an experienced user and get their feedback into your proposals. Even some synchrotrons provide the opportunity to talk to the referees beforehand, right? Or you just contact them. But there's always a chicken and egg problem of, do you need preliminary data or not? Usually you do not have one unless you are an experienced user, and so 60% of your beam time is the thing you promise, and then 40% is just either finishing another project or preparing the next one, right? So this is like the ebb and flow of different projects. You go 3 times a year, and you start the project at the first time and you finish it at the third time. And while most users who go for the first time, they don't have this luxury, right? And the second, chicken and egg problems, both are connected, of course, that lack of prior XAS experience, and there's no way to go around that. And like the synchrotrons themselves, they need successfully finished project in order to motivate governments to keep financing them. Because if you now, if you think about all these large facilities, up to 60 beamlines, and all of them have like 4 to 5 people employed, and then the whole backlog of the electron storage ring, of course, also requires a lot of manpower. And in the end, you're talking about an enormous staff that, I'm sorry, Thomas, but essentially does nothing, but provide the opportunity for users to do their crazy shit. But there's a bright side to all of that. And so I'd say here, try to get to know the people behind the websites and the facilities, because I have yet to meet, let's call it like that, like shitty people in the synchrotron community. Because synchrotron facilities, you do have to, if you are not capable of collaborating with others, you will not make it in the synchrotron community. It's completely impossible to work alone and to not be a good collaborator. So everyone is usually helpful and interested in your success, as long as you reach out to them. And this, of course, includes me and all the other people that are here. And everyone likes to talk, especially about his own or her own expertise. Yeah, I still have time left, so I continue. So far, this was the principal slide, right? And this is all nice and dandy as long as you have a lot of absorption, right? So think of it like that. What is the worst way? I think this is a chemistry example. What is the worst way to measure the weight of the captain of a ship? Measure the ship's weight with the captain and without, right? And this is essentially that. If your absorption is just not big enough, then just measure nothing. So here we have an example of a powder sample, which is very concentrated, and we have to dilute it in order to not saturate everything all the time. And here we have a typical protein sample. Yeah, that's it. Like, this is what the extent of most protein samples you can, the absorption of most protein samples you can prepare that are physiologically relevant and not just extremely over-concentrated garbage or crushed out and whatever. However, as Thomas already mentioned, you always have these relaxation processes afterwards. And these transitions, in this case, the K-alpha emission, usually make up like 90% or more than 90% of the relaxation events. And they are we know the specific energy at which they are occurring. So what we can use then is a fluorescence detector, right? So what we see here is the multi-channel analyzer at, I think this one's Bessie again. And what you can see here is the element we're interested in is zinc. Like, we know at this fluorescence energy, there's the K-alpha emission of zinc. We also see that zinc is not the only thing present in our sample. Like, here we have something that's probably from the cryostat surrounding the sample, some metal. I think it's tungsten. It's not copper as I was thinking, but I think it's tungsten. And then we go down, there's some iron, there's some nickel usually. Then we select the emission energy we are interested in on the element we are interested in. And then we suddenly get a chance. So if you not look at the absorption, but rather the K-alpha fluorescence, we suddenly have a chance to measure our sample, although the, of course, highly concentrated powder sample wins again. But hey, that's it. And this is how it would then, the altered setup would look like. In the bio-XAS part, you would work usually with a cryostat, cooling down your sample, and then an energy resolving detector of whatever kind you would like in a 90-degree angle to the incident beam. Yeah, and this is, for example, a photo of Bessie. I don't know that. He just came back from a beam time there together with me. Isabel as well. So we have some experience. That's actually a question I wanted to ask. Like, who has been to a synchrotron? Who has like touched a computer at a synchrotron? Of course, Kelly, Gerardo, and Isabel. Someone else? Thomas, Mario, of course. Like Mario and I met at SSRL the first time. Yeah? Someone else? Yeah. Martin also. Don't be too shy, Victor, I know. Like, I know all the people I have been there. Okay, great. Someone else? Someone I haven't seen? Yes, all of you? No. Almost all of you, the important ones. Okay, great. Just for me to get an image of what people are present here. And then what to look for in materials and methods. Usually what is mentioned is the insertion device. In this wall of text you encounter when writing a paper or reading a paper. You encounter the monochromator, in this case 311 double crystal monochromator, so higher energy resolution. I of course took a material and method of one of the cooler papers I've been involved. The sample setup, in a way, what cryostat was used, how deep temperature, how low the temperature was the samples were measured at, what detectors were used, and this time then similar to the beamline Thomas, Roland circuit spectrometer, and what form of energy calibration is done afterwards, because essentially without an energy calibration, if you simultaneously, you are to a certain extent lost about the energy you are measuring at. You just need to trust the computer otherwise, and we don't trust computers. And sorry, you want to make a share pause. And how does the reality of that look like? So here we have Martin at the 6.2. Yeah, I think it was the 6.2. And this is the Poucher Institute in Swiss. So here are the different, like these cryostats are essentially like small, long tubes where liquid hydrogen is then used for cooling it down to 20 Kelvin or something like that. And you have these sample holders that can be different for each beamline you're going to. So a rather terrible first error you can make is use the wrong sample holders, and then you arrive at the beam time and like it doesn't fit. And that's very awkward. It's all the wrong cryostat. Yeah, that has also happened. They install the wrong, not the cryostat you asked for, and then it's like awkward, and then you have to change it again, and just waiting there, looking at them work. Yeah, typical errors. But the nice thing about these sample holders is you can cut them out of acrylic foil, and because you're just two-dimensional in any way, so just make these windows closed by Kapton. Thomas, that's a question I have. Kapton is already like half a micron. Kapton is already too thick for LH, for 800 electron volts.
For LHs, you would use like a silicon nitride.
Why is it less absorbing? Is it thinner, or is it?
Yeah, you can make none.
Okay. So don't breathe against.
It's actually surprisingly stable. Like, I mean, the windows are big, right? They're not centimeter by centimeter. Then the windows you're looking at are like a couple of millimeters by a couple of millimeters, or 1 millimeter, or you can have like a mesh of 1 millimeter windows. They're surprisingly safe.
Cool. Thank you. Always curious about that. And ice and why we hate it. We hate it so much. So in the perfect world, we have our sample, the X-ray comes and the emitted K alpha photon is then detected by the detector and everything is great. But the reality usually is you have some form of ice which also reflects, and this is completely terrible. And like the worst example I've seen in my personal experience so far is like that. Yeah, of course, I only showed the cleaned up data, but this was terrible. Like war stories, right? Yeah. And this was then the fluorescence, because what you have here is that the detector is completely saturated. It cannot deal with all the photons, because what you need to know is that the photon flux itself, and these numbers, right? Photon flux itself is what, like 10 to the power of 10 photons per square centimeter and or square millimeter and second, right? And what you're actually detecting in the usual sense is like 10,000 counts. So you lose 10 to the power of 6 counts per second of X-rays, which just go through your sample and never see an absorbing element, right? But once ice comes into play and it reflects maybe 0.01% of the beam, then your detector is essentially being fried. And then you need to clean up the data, and this is the thing you then show your PI and say, look at the nice data I collected. This is what you see then in a group seminars, and this is how it looks before. Usually what you do is you store them without access, like you avoid proximity to water, and then so you store it in liquid nitrogen, or you add a little bit of glycerol to the buffer, except if you investigate copper, because this is a very rare special example where glycerol induces like incredibly accelerated photoreduction, as in this case, where I left the scan running without looking at it, because I was this is just a reference compound. I can go for lunch, and then I come back and I look at this like what the, and then like a month later, Graham George published a paper about glycerol effects on copper samples. Like so what you see here is a very nice example of photoreduction in a copper sample with glycerol present. If you don't have glycerol present, then you don't see that. So you have to look what you have to pick your battle, either you battle ice or you battle photoreduction. And now I'm pretty much on time. That's essentially all of the extent I want to present. Any more questions or applause? I'm also happy with applause.
It's not a question, it's a remark. I think it's a very nice overview of everything that you should do or maybe not do as well with synchrotron, and a very nice summary of what you could do. I like to see a synchrotron absorption spectroscopy as a always tells students. It's the same as you small UV spectrometer that you have on your table or in the lab for practicals. See what I mean? It's the same with 10 meters more. You know? And but the principle is exactly the same. You have photons, you have a sample, and you detect the photons. So in principle, it's so easy. You know, it's so straightforward. I mean, a spectrophotometer for practicals is very cheap. It's a few $100. It's nothing. It's exactly the same, but what makes it very difficult to handle is X-rays, because you are not in the visible spectrum, you are in the X-ray spectrum. And that really screws up everything. It screws up your optics, your samples, and your detectors, because everything in the X-ray regime becomes small. But if you think of an absorption experiment as a simple UV experiment, then you get the rough idea, except that it's not the same energy. And that makes all the difference. I think that's important.
Krista. Any other question or comment?
Anything on YouTube?
Oh, I should check.
Why does glycerol have the effect of reducing the ice scattering?
So no one knows really. That's usually the extent of it. Like X-ray spectroscopists just want to avoid photo reduction, so they just once they have it, they adjust the experiment. But I've talked to a theoretician that actually models absorption events from X-rays on different solvents, and he said that the energy, it's just a weird coincidence that at the energy at which copper absorbs is also an energy at which glycerol absorbs, and then CO gets a CO bond is broken. And with the radical you create in that sense, because like if you take an X-ray sample before you put it in the X-ray and put it into an EPR, and it's EPR silent, let's say you have no EPR. Then you put it 1 minute into an X-ray source, and you put back into an EPR, you have radicals all around. But for some reason, the glycerol radicals are just way worse than the radicals you create in water. I'm not entirely sure why, but there's a weird coincidence between copper. And also copper likes to be reduced if it has a possibility. It's like so close to D10. It's like, if I only could get one more electron.
Okay, we have a question from YouTube. Rocio Mesa Gordillo asks if this can be used to distinguish sulfur species.
Yes. Yeah, come back tomorrow when Kelly gives a presentation.
Because most of my stories about sulfur edge are making libraries at this point of biologically relevant stuff, but absolutely you can use this for sulfur species. The one caveat is that it's most commonly used for simply edge studies at this point. So you can have sort of presence, absence. It'll be very important to bring model complexes or to have a library of such things so that you can tell, what's bound to it, what state it might be in. But on the horizon, which I'll talk about some of the conditions you have to take care of, we can start approaching sulfur excess, but it's going to take a while. Everything absorbs basically at that low energy.
You can also do sulfur KH, right?
Yeah. That's what we we had like this beautiful double beam time set up, and then the pandemic hit and we had to cancel 2 weeks of it. First copper and then sulfur, and it's like so nice the experiment, and no.
That's the other thing, you want to combine it with your metal edge, whatever your transition ion or transition metal is, then you can compare that to the sulfur edge and see where you're working with. Yeah.
Okay. No, that's I'm not sorry where to face, but that's a great question.
So hopefully Rocio was listening. If there's another question. Any more questions from the audience here? No?
I'm not disappearing in a second, and we are all still remain, so we can. So now on the program.
So let's thank Niels for this presentation. Now we'll pass to the.
Now we pass to the hands-on session, which will not be recorded anymore because it's just.
Yeah.
Yeah, but I would like to do that without YouTube watching. Like,
okay.
Just be able to present in the dirty, like the kitchen stuff you usually do not see. Yes, exactly. So we say goodbye to all the YouTube watchers and Until tomorrow, of course, yes. Very exciting talks. Okay. And are we offline now? Now we can take out the tequila without anyone watching. No, we're not doing that. You're not doing that, Dr. Museo, if you're watching. Yeah, so the